Back in 2010, JetBrains, a developer of programming tools, had a problem. Adding features to their products, including the award-winning IntelliJ IDEA, was growing increasingly difficult, and they felt that Java was the cause. Java at that time had gone years without a new version, and its syntax was always a challenge for programmers. After investigating other JVM languages, JetBrains made the bold decision to create their own. That language, Kotlin, debuted in 2011 and was officially released in 2016. Kotlin's concise syntax, null safety, and Java compatibility have made its popularity explode. In 2018, Google made Kotlin the preferred language for Android development. But Kotlin can do more than just build Android programs. It can replace Java anywhere, in apps and on the server. Plus, Kotlin can compile to JavaScript for web browsers and Node.js. And a feature still in development at the time of recording lets Kotlin build native apps as binary executable. We'll start with the basics and cover all of the essential features along the way, like classes, Lambda functions, and even coroutines. To get the most out of this course, you should have some programming experience, preferably with a curly brace language like Java or C#, but any coding experience is helpful. This course is for beginner Kotlin programmers. It starts with the most basic concepts and advances to cover some more complicated things like coroutines. You will learn the language more thoroughly if you follow along, code the examples yourself, and complete all of the challenges. We'll use the community edition of IntelliJ IDEA for this course. Kotlin development is possible with most popular editors, but IntelliJ is free and includes tools to make programming delightful. You should also be comfortable installing applications on your development system. And most of all, you should be ready to learn a new language. Hopefully, by the end of this course, you'll understand why I think Kotlin is so awesome. JetBrains released IntelliJ IDEA in 2001. Since then, it has become one of the most popular and awarded Java IDEs. The name, for the curious, is a combination of JetBrains' original name, IntelliJ, and Integrated Development Environment Application. Most devs call it IntelliJ. Since releasing IntelliJ, JetBrains has added numerous developer tools to its suite, so many that it recommends using its Toolbox app to install and update them. Since we are only installing IntelliJ, let's skip the Toolbox and head directly to the download page on JetBrains' website. IntelliJ has versions for Windows, Mac, and Linux, and comes in two flavors: the feature-packed and paid Ultimate Edition, and the free Community Edition. Luckily for us, the free version has everything we need to begin programming in Kotlin, including Java. Make sure that the page has correctly selected your operating system and click the Community Edition download button. Once the download is complete, launch the installation program and follow the instructions. If you have a 32-bit version of Windows, you will unfortunately have to do more work. IntelliJ comes bundled with a 64-bit version of Java, which is incompatible with your system. JetBrains recommends that you contact their customer support found on their help page on their website. The Start menu of IntelliJ IDEA presents four choices: Create New Menu, Import Project, Open, and Get from Version Control. Click Open and navigate to where you save the exercise files and click Open. The exercise files are available from this course's webpage on the LinkedIn Learning site. And so I'm going to navigate there and then click Open. If you see the prompt, IntelliJ IDEA found a Gradle build script, it is very important to click the link Import Gradle Project. And if you get this build window at the bottom, you can easily close it by clicking the dash right there, and then that window goes away. Now, with your project loaded, the left side of the screen is the project menu. The right side is the code editor. Let's go ahead and open a file. So we'll go into Open Exercises, Open Source, Open Main, Kotlin, and then let's just open up Chapter 2, 01, Begin. A Kotlin application can have more than one main function, and it doesn't have to be in a class. We'll take advantage of this capability as we work through the exercises. To launch our code, we'll click the green play arrow located to the right of the main function declaration and click Run. Now we're ready to write some code. To create a variable in Kotlin, begin with the val or var keyword. So we're going to come up here, and we're going to say var, then the name, which is count, a colon, the type, which is going to be int, the equal sign, and then a value, which is going to be 0. The var keyword creates a mutable variable, one you can change. The keyword val creates an immutable variable. Its value is settable only once. Using immutable variables is a programming best practice, so declare them whenever you can. So let's create a val. So val number colon int, and we're going to say equals 42. Some parts of the variable declaration are optional. If you assign a value to a variable, usually its type can be inferred, so you can omit it. So we'll have val other number equals 43. Kotlin has 4 integers in a range of sizes. The default type is int, which is 32 bits and has a rough range of plus or minus 2 billion. If you omit the type declaration and the number falls within this range, then int is inferred. The int has a 64 bits big brother, the long. The final 2 integer types are byte and short, which have 8 and 16 bits respectively. Kotlin never infers these two since they are in the int's range. If you want them, you've got to ask. So let's declare a long. We're going to say val my long and colon long, and it equals 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Give it a bunch of zeros and an L to specify that it is a long. For byte, it's val my byte colon byte equals 127. Then we have val my short colon short equals 32767. In addition to integers, Kotlin has 2 floating point types, the float and the double, which is the default. If you want the 32 bits float, you must specify it and append an F to the number. So let's create a double, val my double colon double equals 98.6. And for a floating point, we're going to say val my float colon float equals 12.2, and then we need to put an F. And let's create one more double, val also double equals 101.5. Kotlin is very picky about number types. It won't automatically widen numbers like most languages. If a function takes a long, you can't send it an int, even though such a translation is usually safe. Luckily, every number also supports quite a few conversion methods. So we have val as int, and we're going to say also double dot to int. And so that's going to turn our double into an integer. And we say val as float and equals my long to float. One surprisingly helpful convenience is the support of underscores as number spacers. Especially when I have large numbers, the underscores make it much easier to enter the values correctly. So let's enter maximum int. So that's going to be val max int equals 2 underscore 147 underscore 483 underscore 648. Kotlin supports hexadecimal, binary, and long constants. Add a capital L to the end of a number to make it a long. Prepend a number with 0x for hexadecimal or 0b for binary. Like all modern languages, Kotlin has robust support for a variety of numeric data types. If you'd like more information, please check out the Kotlin online documentation. Immutable data is a concept whose popularity has grown explosively in the past few years. If you happen to be a programmer of a functional language like Lisp, Clojure, or F#, you're probably wondering what took the rest of us so long to get to the party and that we haven't gone far enough. Earlier in this course, we said that Kotlin has two types of variables, val and var. We also added that val is preferred and considered a best practice, but we didn't explain why. Now is time for an explanation of immutable variables and 3 reasons why you want them. 1. Legible code. The first benefit of immutable variables is that they help make your program more legible and comprehensible. I think of keeping track of variables like juggling. I know it sounds a bit silly, but stick with me. When juggling, I need to keep track of each ball, where it is, and where it is going. With variables, I need to know who creates it, who can read it, and who can modify it. Bugs in code aren't usually caused by creating or reading variables, they're caused by changing them. Every variable that can change increases the complexity of your program, just like adding a ball increases the challenge of juggling. Using immutable variables makes your code more straightforward and easier to understand. 2. Testable code. Immutable variables are one of several techniques that can help make your application easier to test. Others include writing pure functions, using single-purpose classes, and minimizing state changing. Covering them is out of the scope for this course. If you'd like to know more, you can check out the course Software Design, Code and Design Smells by Harrison Ferrone on LinkedIn Learning. 3. Thread-safe code. Perhaps the most significant benefit, one which will aid you the most as you grow your Kotlin confidence, is thread safety. One of the big problems in multi-threaded code is when a variable you are working with gets changed underneath you by another thread. Finding and resolving this issue is extremely difficult. It is far better not to have the problem in the first place. Immutable variables can't change, so that is one less thing you have to worry about as you make your app thread safe. Kotlin provides us the char and Boolean types for working with character and Boolean data. Let's begin by checking out char. Declaring a character is simple. It is like any other declaration except it specifies the char type and encloses its data in single quotes. We can also encode ASCII data by using the / escape sequence, and there is support for Unicode characters with the \u encoding scheme. Let's create a few character variables. So we say val letter char equals single quotes a. Let's infer an ASCII character. So we say val tab equals single quotes \t, and this is going to be the tab character. We can create Unicode characters as well. So we say val infinity equals single quotes \u 221 and then capital E. And let's go ahead and print out our characters. So we're going to say print line. Then we do double quotes, letter equals $letter. Then we say print line, double quotes, tabbed, then a space, $tab, another space, and then over. Let's move up the screen just a tad. And then we'll go print line, double quotes, infinity equals $infinity. Keep in mind that Kotlin never does implicit conversions and that characters are not numbers. Conversion methods can convert to and from character types. So we'll say that val line feed equals the number 10 dot to char. We'll do a print line, double quotes, line feed equals $, line feed, space, next line. And let's uncomment the line demo char and run the code. And everything looks as expected, including the line feed, which caused the line to break. We have a printing of the infinity character, and we can see that our tab has tabbed over on the second line. The Boolean data type is also simple to declare. A Boolean can have one of two values, true or false. So let's go in here and comment out demo char and comment in demo Boolean. And right inside the demo Boolean, we will say var will exercise Boolean equals false. Now we can shorten the declaration using inference, and because we're already saying that it's equal false, we don't need the Boolean, so we'll delete that, and we'll delete the colon. We can also assign a Boolean the results of a logical expression. So we'll say that val big number equals 1 underscore 000 underscore 000. So big number equals 1 million, val small number equals 2. And then what we'll do is we'll do a print line and say is big bigger, and say equals $, curly braces, and inside of here we'll do a logical expression, big number greater than small number. And let's go ahead and run the code. And we get is big bigger, and it prints out a Boolean true. The OR operation returns true if either operand is true. It also short circuits. A short circuit means it doesn't evaluate the second operand if the first returns true, hence the name lazy disjunction. It is lazy because it only does as much work as necessary. Programmers sometimes assume both operands are always evaluated and find this behavior surprising, so it occasionally causes bugs. The AND operation returns false if either operand is false. If the first operand returns false, the operation short circuits and the second operand is not evaluated. So near the top of the file, there are two functions, first operand and second operand, which return false and true respectively. If we place first and second operand into a logical OR expression, both operands are executed. So what we're going to say here is if first operand, and then we do an OR, which is the pipe symbol twice, and then we do second operand. Both of these operands will execute because the first operand returns false, and so it needs to check the second operand to see if it returns true. And so we can print here, print line, at least one operand is true. Now, when we place them into an AND logical expression, only the first is evaluated because first operand returns false, making the entire expression false. So we can take this guy, we can copy him and place him below and replace the OR symbol with the AND symbol, which is the double ampersands. And then we need to change this expression because both operands have to be true for an AND to be true. And finally, we can negate any Boolean symbol by placing an exclamation point in front of it. So we'll say print line will exercise equals $ curly brace exclamation point will exercise. And let's run the code. And We get the results as expected. We've got both of the operands were executed for the OR operation. And so we got the message, at least one operand is true. For the AND operation, we see that the first operand executed, because it returned false, the whole expression is now false. So the second operand did not evaluate. And finally, we get will exercise turns from false to true because we put the negation on it. And this has been a look at the char and Boolean data types. The Kotlin online documentation has more information if you need it. Text processing is one of the primary duties of computer applications. Strings in Kotlin, like most modern languages, are feature-packed. Let's explore them. We create strings like creating other types, and again, specifying the data type is optional. So let's create a string. We're going to say val greeting :string equals hello there. And let's create one more variable, not a string, and we're going to say O equals 50. We can use templates in strings to display the value of a variable or Kotlin expression. Place the variable inside of the double quotes with a $sign in front of it. For more complicated items, surround them with curly braces. Don't go crazy with templates though. Having too much code in a string makes them hard to read. Consider pulling the expression out and assigning it to a variable. So now we're going to say, create another string, and we're going to call this string Janet, and it's going to equal double quotes IO Janet \$, and that is how you print a $sign in a string. And then I'm going to say $O dollars, and then we'll print that out. We can render both ASCII and Unicode characters in strings with / escape sequences. So we'll say val infinity equals the infinity symbol is \U 221E, and print that out. Strings have a large number of functions, properties, and extensions. The simplest is the length property, which returns the size of the string. So print line, and we got double quotes, and then we have square brackets, and inside of that we're going to say $, greeting is $, open curly brace, greeting dot length, and space and characters long. We can retrieve the character at a specific index with the get function. It is an exception if the index is out of bounds, so be careful. Indexing is preferred and offers identical results with a more concise syntax. So we say var bad equals greeting dot get 2, and val letter equals greeting, and then we're going to do an index of 1. We can compare two strings with the compare to method. The returned integer is 0 if the two strings are equal, a positive number if the first string is greater, or a negative value if it is lesser. So we say val compare 1 equals beta. Let's move up the screen just a little bit. Val compare 2 equals alpha, and print line $, curly braces, compare 1 dot compare 2, and then inside of the parentheses we put compare 2. The subsequence function allows us to retrieve part of a string. This method always creates a new string, even if it is empty or only has one character. So we say val sub equals greetings dot sub sequence, and we're going to say 6, 9. And do a print line, double quotes, sub equals $sub. Because strings are iterable objects, we can use them in loops. We haven't covered loops yet, but here is how we can print out each character one at a time. So we say for single in greeting, opening curly brace. Then we're going to do a print. And in the print, we're going to do a double quotes, $ single, and a space. If we need our string to be multiple lines long and include characters like the line feed, we can create a raw string. Raw strings are wrapped with triple quotes. When printed, they display everything between the triple quotes. So we're going to say that val my string equals 1, 2, 3 triple quotes, and we're going to get rid of the trim indent, and we're going to say that Kotlin is fun and Kotlin is pragmatic. Then we're going to do a print line and my string. Now let's run the code. And we find out that I owe Janet $50, the infinity symbol, that there are 11 characters in hello there, that characters 6 through 9 of hello there are the. Here is hello there one character at a time with a space in between, and here is our raw string. String manipulation is often the source of performance and memory issues in programs. Kotlin strings, like those in Java and other languages, are immutable. This time, our explanation of immutable is somewhat different than it was for variables. Kotlin never changes the memory allocated to a string. Instead, it creates a new string. If you're doing a lot of memory manipulation, you should look at the String Builder class in the official documentation. This class does highly optimized string manipulation. Hopefully this section has shown you some of the cool stuff we can do with strings in Kotlin. Please check out the Kotlin documentation to discover more. It would be easy to assume that Kotlin is only an enhancement of Java, and that is an understandable conclusion that many programmers new to it reach. In this section, we'll look at a few of the things that make Kotlin a better language than Java. Let's begin with a subtle difference, which is nonetheless a key to understanding Kotlin: its preference for expressions instead of statements. To understand why this difference matters, we first need to understand what exactly are statements and expressions in the context of programming languages. Here is the Wikipedia definition of a statement. In computer programming, a statement is a syntactic unit of an imperative programming language that expresses some action to be carried out. And also from Wikipedia is a definition of an expression. An expression in a programming language is a combination of one or more constants, variables, operators, and functions that the programming language interprets and computes to produce another value. These definitions are dry and scholarly, but the key things to understand are that a statement produces an action, while an expression produces a value. Many of Kotlin's keywords are expressions, unlike their statement-based brethren in other languages, making it possible to write code which is both clear and concise. One of the things that Kotlin newbies notice is the lack of the ternary operator. C popularized the ternary operator decades ago, and every similar language has included it since except Kotlin. Why? Kotlin doesn't need it, since if is an expression. It can return a value, which makes the ternary redundant. We'll cover the if operator in detail in an upcoming section, but here's a quick preview. Now, this commented out section of code is a ternary operator. It consists of a Boolean compare. It returns the second operand when true, otherwise the third operand. We can do the same thing using if. First, we add the operator. Let's go ahead and comment this back in. We add the if. we surround the expression with parentheses, get rid of the question mark, we replace the colon with an else, and that's the same thing using Kotlin's if expression. Let's go ahead and line that back up. Kotlin also has the when expression that you can think of as a turbocharged version of the switch case statement, which allows us to write code like this. So we have val age equals 35, val boarding group equals when age, and then we need some curly braces. Inside the curly braces, we do in 0 : 18, and that'll be part of the family group. In 65 to, let's be real optimistic, to 200. Puts you in the senior group. And then to cover all the other expressions, we have an else. And then just regular boarding. And we can do a print line. Print out which boarding group you're in. Group. In Kotlin, like in JavaScript, all functions return a value, making all function calls expressions. If the return value isn't explicit, then the result is unit, which is Kotlin's equivalent to void in other languages. We can assign it to a variable and print its value, which is Kotlin.unit. So at the top of the file, we have a function called returns nothing. And we're going to say val from nothing equals returns nothing, make a call to it, and then print out its value. Kotlin doesn't allow a few common expressions. In Java, the assignment operator is an expression allowing us to do multiple assignments like this. So we can say val A equals 100, val B equals 101. And again, this won't compile. We could say A equals B equals 98. Now, what this is trying to do is assign 98 to both A and B. Here, we try to assign 98 to both variables. In Kotlin, the assignment operator is a statement, making this an error. Kotlin doesn't allow declaring multiple variables in a single statement either, but that restriction is more based on grammar. Okay, let's run the code and check out the results. You are in the regular group. Returns nothing function is called. Kotlin unit is returned. All pretty much as we expected. Expressions allow us to write code that is more fluid and easier to understand and test. Take advantage of Kotlin's expressive nature wherever you can. Let's take a closer look at the if expression. We'll begin with our equivalent of the ternary operator. Start off with a couple of variables. This snippet shows a few essential elements in a compact package. First, we can assign the results of an if expression to a variable. Next, the result of the expression is the value returned by the last clause evaluated. And finally, we must define an else clause for the expression to be complete. Now let's take a step back and make sure we fully understand the if expression. The simplest version of the if executes a code block when the expression is true. The code can be either a single line of code or as many as necessary wrapped by curly braces. We can add more test cases to the if by adding else if clauses. Keep in mind that if the test cases overlap, the first match wins. In this code snippet, even though the number is greater than 100, it is also greater than 10, which comes first and wins. So always use an extra bit of care when writing ifs with multiple clauses. And finally, we can cover any remaining cases with the sometimes optional else clause. So far, the if expression works the same as it does in any other language. When used as a genuine expression, things get different. There must be an else clause. Every branch must return a value, and the expression returns the last value of the executed branch. Let's create another number. The if expression is very flexible. You can even have each branch return a different type. One branch could return a string, another an integer. Of course, you have to write your code to handle this flexibility. You should also alert the compiler and IntelliJ of your intention and make the variable of type any. That way you won't get any pesky compiler warnings. So let's go back up here and say : any. And now more of our compiler warnings disappear. And move down. Just because you can make something an expression doesn't mean you must. Imagine you need to set a variable true if another variable is over 100, false if not. Your first reaction might be that this would be a perfect use case for the if expression. So if we have val is greater, but if you look again at the code, we are returning true or false from a Boolean expression, which also generates true or false. We can instead set the variable to the results of the Boolean expression. We don't need an if at all. Sadly, I occasionally see this in code reviews. So we can just get rid of the if and the parentheses and everything on the other side of this parentheses and just set greater to that. If expressions are a great tool, but quickly become cumbersome when the number of clauses grows to 3 or more. In general, when you find yourself writing too many clauses, you should consider using the when expression instead. So let's go ahead and run this. And let's see, we get our string here. We get greater than 10, which we expected because that's the first clause. And we get it's greater than 100. So we get the alpha, the string being printed there. And that's pretty much everything in that code. The Kotlin when expression is powerful. While often compared to the switch case statement in other languages, the when expression can do much more than they can. Let's find out together. We'll begin by emulating a simple switch case statement. We add the when operator and a variable. So we'll say first off, val x equals 1. Then we say that when x, then we have an opening curly brace and a series of branches, each with a comparison to match, an arrow, and code to execute. So we say 1, and then the arrow is a dash and a greater than sign. Then we do a print line and say x equal 1. And we do the same thing for 2. And we say x equals 2. For simple actions, the execute code can be a single line. If 1 is not enough, you can wrap as many lines as you like in curly braces. There is no way to have code fall through from one match to another. In the switch statement, fall through was usually accidental, and it was the source of bugs. Typically, the flexibility of the when makes intentional fall through unnecessary. As an example, if we want both 3 and 4 to execute the same code, you can put them in the same matcher. So we say 3, 4, then the arrow, and print line x equal 3, or 4. When there is no match for the value, no action executes. The when has an optional else branch that runs when there is no match. If we assign when to a variable, the else is mandatory unless we have an exhaustive list of branches. For instance, if we are checking enums or a sealed class and provide a match for each member, we don't need the else. So if we say that val card equals suit dot spade, and we say val y equals when card open curly brace, and we say that suit dot club comma suit dot spade, then we have the arrow and we say print line black card, then we say suit dot diamond comma suit dot heart, an arrow, and print line red card. Now, because I did that, all of my little squigglies went away because Kotlin knows that I've done an exhaustive list of everything that's up here in this enum class. Kotlin's when is not restricted to just integers. You can compare virtually any type. We can compare strings, and I'll say val, and I'll just pick a name at random, equals Troy, and then say val last name equals when name, open and close curly brace, and I'll say Hatan, and return, and I'll say Todd. So if it finds the first name of Todd, it will return the last name of Miller. And I'll have, if it finds Troy, we'll return the last name of Miles. Now notice the when still has red squigglies on here, and it says when expression must be exhaustive. Add necessary else branch. So I will add else, and then we put the arrow, open curly brace, and I will assign this the string unknown. And then down here we'll say that print, and we'll say $ name space $ last name. Since we haven't included an exhaustive list of strings, which would be difficult, we must include the else. We are returning a string from each branch. Just like with the if, the else returns the last value of the branch. We can replace individual values with a range. A range is simple to create. The first number specifies the beginning of the range, then 2 dots, and then a number to mark the end of the range. The only twist here is we need to precede the range with the membership operator in. So now we're going to say that value age type, and I'm going to bring things up from the bottom of the screen, and it's going to equal when x, open and closing curly brace, we're going to say in 0 dot dot 1. And this is going to return baby in 2 dot dot 4. And we'll say toddler in 5 dot dot 12. And this will be a kid in 13 dot dot 19. Teenager in 20 dot dot 64, and this is going to be adult. And finally we're going to have else arrow senior, and then we'll do a print line you are a $H type. Now let's run the code. And we get x equals 1. We get a black card, and that's because it's a spade. We get Troy Miles And because x is 1, we get you are a baby printed here. There are still more tricks we can do with the when expression. Be sure to check out the official Kotlin documentation for more information. We've revealed a lot of Kotlin's superpowers. Now, we come back down to earth. Loops in Kotlin are pretty standard. If you are familiar with them in any other programming language, you're most of the way there. And if all of this is new to you, no worries. We'll show you that loops are nothing to fear. Let's begin with the for loop. There is a slight twist here. The old C-style for loop doesn't exist in Kotlin. I used to call it a three-parter. Let's actually show it. It had an initializer, a comparer, and an incrementer. Unfortunately, it was also the king of bugs. Kotlin has followed the lead of other languages like Java and C#. They both have a for each, which only works with collections, which tends to reduce the bugs. Since Kotlin doesn't have the three-parter, for is its name. Let's count from 1 to 10 with it. Once again, we are using our good friend the range here. Notice how there is no confusion in our code. Our range is from 1 to 10, and I only has those values. We don't have to compare anything. This loop is always my go-to, and it will probably be yours too. If you are iterating over a collection, the loop actually gets simpler. So let's create a collection. Now, students. We haven't covered collections of any kind yet, but trust me on this. It is easy to iterate over our students. It isn't a rule, but typically our collection is plural and the current item is singular. So we get a student from the students and print it out. Easy peasy. You may be wondering, how do you get the current index? You don't have to do something kludgy and error-prone like setting a counter to 0 and incrementing it. Kotlin has you covered. It keeps an index internally, and you can get access to it and the current value by using the withIndex method. This method will return a tuple containing the index and value. The reason that we wrap index and student in parentheses is to destructure their values. The index is always 0-based, so you'll have to add 1 to it if you need 1-based. The other loops are the familiar while and its cousin, the do while. Most of the time, you'll use the while, but if you ever need to guarantee that the body of the loop executes at least once, go with the do while. With both of these loops, always double check yourself to be sure the loop will end someday. I've seen code get stuck in an endless loop that was making calls to a paid cloud service. It is no fun when something that should have cost only a few parts of a penny ends up costing real money. The final things we need to discuss are break and continue. Both come from the C language and the dawn of time. The break statement causes an immediate loop exit, and continue skips the current iteration and goes to the top of the loop. As old as these two statements are, programmers forget about them and end up writing complicated logic to do something that a break or continue could have done in a much more straightforward way. And let's go ahead and execute this code. All right, we have our counting to 10. We are iterating through our students with an index. We're showing the while loop, which is counting down from 5, the do while, which is counting up, and then we have our break, which will stop at the first even value. So it says 5, and then when it gets to 4, it stops. Choosing which loop to use is not difficult. If the loop must execute at least once, use do while. When the loop executes until some outside event occurs, you probably want a while loop. And for everything else, especially collections, you want the venerable for loop. Null pointer exceptions are common bugs in modern programming. One of Kotlin's primary design goals is to make it possible to eliminate these bugs. Kotlin has many tools, but you have to do your part to get rid of null pointer exceptions. Let's explore the different items in Kotlin's toolbox. The first way Kotlin helps you eliminate null pointer exceptions is with its type system. Only nullable types can hold null. Many languages allow a string variable to hold a null value, which means that they then must always check to see if a value is a string or a null. Kotlin is different. Only nullable types can hold a null. You define a nullable type by adding a question mark to the end of a non-nullable type. So here we have a val person1, which is of type person. If we try to make this null, it won't let us. And the red squiggly says null cannot be a value of non-null type person. So this won't work. On the other hand, if we say val person2 colon person question mark, we can set it to null. Kotlin keeps track of nullable types. If we have a nullable string greeting and try to access its length property, we must check for null first. If we don't, it is a compile time error. Kotlin tries to protect us from ourselves. It is much better to have a compiler error than a runtime error, one found by our customers. Once we have checked for null, the compiler lets you do whatever you'd like to the variable. So we have a value, greeting, make it nullable. We'll check to see if it's null. And because we're checking already for null, we can just use the value here. One quick aside, if you try to print the null string without checking, the compiler won't complain since it is a legal operation. One of the coolest ways to eliminate the dreaded null pointer exception is the safe call operator. To use it, insert a question mark before the dot when accessing any property. So here, we're going to say print line greeting length equals you notice that if we don't do the safe call operation, it gives us a warning. Warnings are always read in IntelliJ, and it says only safe or non-null assertion or calls are allowed on nullable receiver of type string. So if we put in our question mark for our safe call operator, we are now allowed to do that. Now, if our variable is null, it prints null. Not exactly useful, but better than crashing. Another factor that increases the coolness of the safe call operator is that you can use it as many times as necessary. This is especially helpful when you have to drill down into a complicated nested object. The Elvis operator is a handy companion to the safe call operator. It returns the expression on the left if it is not null. Otherwise, it returns the right side. Also, if the left expression is not null, the right is not evaluated. One common usage is as a default value. So here we can say val len equals greeting question mark dot length. And then we do the Elvis operator, which is a question mark and a colon, or it's 0. There is another operator you should know, but it is not for the faint-hearted. The not null assertion operator. Like the safe call operator, you place it before the dot when accessing an object's property. It consists of 2 exclamation points. If it seems like they are screaming at you, that is because they are. When you use this operator, you tell Kotlin, leave me alone, I know what I am doing. So we do 2 exclamation points, a dot, and then we get the length. Now this code will crash if greeting is null. One last tool we'll cover is safe cast. I rarely need to cast a variable from one type to another, but when I do, I hate having to wrap everything neatly in try-catch blocks. Safe cast allows you to cast, but it returns a null if the cast is not allowed. Let's go ahead and run our code. And if we have hello set to a value, everything works as expected. We get the Joe says hello there. The greeting length is 11. It's 11 again. And if we make this null, and we'll comment that out and run our code. The if block doesn't execute. Greeting length is null, since that is greeting's value. The length is 0, since the Elvis operator uses the default value, so it uses this 0. And we get an exception because the not null assertion operator fails here. So we told Kotlin we knew what we were doing, and unfortunately we didn't. And we get a null value here, and so we get an exception. And lastly, we have the safe cast here. There are more things in Kotlin's null safety toolbox that we haven't covered. Be sure to check out the online documentation. Now it's time to show what you know in a little challenge. In this chapter, you've learned about the if and when expressions. Whenever if expressions get complicated, we prefer to use the when instead because it is easier to understand. In this challenge, you need to replace a complicated if with a clean and succinct when. The code currently executes and must run and return the same output after you improve it. If desired, you can go back and review the previous sections. This challenge should take you about 5 to 10 minutes. Good luck. Welcome back. Hopefully you've completed the challenge without too many difficulties. Let's walk through my solution to the problem together. Don't worry if yours isn't identical to mine. So long as you follow the rules, everything should be okay. We begin by replacing the if with a when. So here's our if, change it into a when, and adding card points as the parameter. Then we change each Boolean expression into a matcher and transform the comparison into ranges. So here I'll put one curly brace. Say in 0.999. And because this is only one string, let's go ahead and just shorten that up to just Perl. Do the same thing here with silver, which is going to be in 1000 ... to 4999. And for gold, it's going to be 5_000 ... 9_999. And finally, we have else. And then all the other code should be identical. So let's go ahead and run this. And we have 7,000 points and we're at the gold level. So here's our 7,000. Here's our gold level. Hopefully you got results similar to mine. Some of you may have realized that the IDE could make all of the changes for you. And quite honestly, I think that is fine. I tend to use all of the tools of my editor when I am writing code. But it is important to know how to do it yourself. We can use an array when we need to store a fixed size collection of items. Arrays have fallen out of favor in modern programming to lists for reasons which we'll explain later. The essential difference between arrays and lists is that we can't resize arrays. One of the ways we can initialize an array is with the convenient arrayOf function. It accepts a variable list of parameters which become the items of the array. So we can create an array by saying val things equal array_of, and give it some values. Interestingly, the items don't need to be homogeneous. We can mix primitive types like integers and doubles with objects. The array includes the get and set functions to retrieve and set items respectively, but usually we use the more convenient index_of operator. So we can change one of the items in our array by saying things of 0, and we're going to set that to 0, the word, instead of 1, the number. Then to display our array, we're going to say for thing in things, and then just print each line out. If you'd like the items to be of a single type, append the type in angle brackets before the parameter list. So now we'll create an array of students. And now we put student in angle brackets. Then we initialize it with student. And let's just create 2 students. And we can change any of those students just like we did before by saying students, use the index operator, and then change it to a different student. And once again, we can print those out. Student in students, and then print each one out. In this example, we make an array of student objects. We can still change any of the items in the array, but it must be to another student object. Another way that we can create an array is with the array constructor. We pass it the size of the array and a function that initializes each value. The initializer function can be either a lambda or an existing function. To pass an existing function, use the member reference operator, the double colons. So down below, we have a function called fiver, and we're going to use that to initialize our array. We say value 5s equal array, and we want it to be 5 long, and we're going to use the member reference operator, the double colon, and fiver. And we'll print each one out by calling 5s. And we'll use a function that we'll talk about later called for each on it. And we'll print each one of these out as well. Arrays have a few associated properties. First up is the size property, which gives the number of elements in the array. So we'll do a print line. We say 5s has a size. Next, we have the indices property, which holds a range, which is the valid indices of the array. So we can print that out by saying print line indices equals. Once again, we have the $, curly brackets, 5s dot indices. And we can retrieve the last index of the array with the last index property. And we have the $, curly brackets, 5s dot last index. And let's go ahead and run our application so we can see what everything looks like. So first thing that we're doing is we're iterating through the things array, and we go from 0 to 3. Then we iterate through our students array. So we get Todd and Daisy. Then we go through our fives array. So we go from 0 to 20. We have 5 elements in it, and their indices are from 0 to 4. And the last valid index of the fives array is 4. Arrays always box values. This is one of the reasons lists are preferred. Boxed means that each element is always an object, never a primitive, even when holding, for instance, an integer. Boxing makes accessing the value slower. There is a primitive type of arrays that don't have the boxing penalty. They're named for their primitive type combined with the word array. So there is an int array, the byte array, the short array, and other primitive types. Each array has a corresponding creation function, int array of, for example. So if we wanted to create an int array, we would just do this. We'd say val p ints equals int array of, and then we could say 1, 2, 3. Keep in mind that there is no inheritance relationship with the standard array. These types are like arrays for developer convenience. While lists are the most popular type of collection, arrays, especially arrays of primitive, are making a comeback. Programmers looking to improve their app's performance have discovered that primitive arrays run circles around their list cousins. We use collections to group elements. Kotlin has 3 main collection types: lists, sets, and maps. Which of these types you choose depends on your task. Choosing the right type can make a massive difference in the performance of your application. By the way, arrays are not part of this group, even though they have many similarities with lists. All of the collections come in 2 varieties, read-only and mutable. Read-only provides us with ways to access items, but we can't add or modify them. Mutable collections give us ways to add and modify the elements. Neither of these has anything to do with the val or var variable types. I like to think of collections as boxes that hold lots of elements. The collection type dictates how it holds the elements. Maps keep them one way, sets another, and lists yet another way. If the collection is read-only, it means once you put the items in the box, you can't take away any or add more. Likewise, with a mutable collection, you are free to play with the items in the box. And finally, the variable type. With a mutable var type, I can point at any box of items I'd like, but with the val type, I can only point at my original box. We'll begin by exploring lists. They are the most popular of the 3, but that doesn't mean they should be your only choice. A list is an ordered collection of elements, each accessible via an index. Let's begin by creating a list of names using the list_of method. We pass the names as parameters to the method. So let's add Daisy, Matan, Rob, and Chenny. If we'd like to print the first name, we have 2 choices. We can use the get method or the preferred index assessor. We need to use curly braces with either to properly access the variable in the string template. So we say print line. The first name is $ curly braces names dot, and we'll say get, and these are 0 base, so we're going to get the first one with the get 0. Likewise, we can get the first name with get, and these should look exactly the same when we're done. And now we're going to use an index, and index is 0. Since our list of names is read-only, we can't add or remove elements, but we can create a new list from it. The sublist method allows us to create a new list from an old one. We state the begin and end indexes, and it creates a new copy. So var sub names equals names dot sublist. We give it a begin index 1 and an end index 3. And we can print all of the names that it holds with a print line sub names. If we need the ability to add or modify elements, we must make a mutable list using the mutable list_of method. We can pass a list of objects, as initializers or add the items individually. So in this case, we're going to call our list items, and it's going to be a mutable list of, and let's just give it a bunch of numbers, 2, 4, 6, 8, 10, 10 again, 10 one more time, and 10 one more time, and 14. And we're going to change the first one by saying items sub 0 is equal to 1. We use add to add items. We delete items with the remove and remove at methods. The remove at method deletes the item at the pass index. The index value must be within the bounds of the list, or it throws an exception. The remove method deletes the passed item from the list and returns a Boolean true if it was successful. So we can say items.add. We're going to add the number 12 to our list. Let's go ahead and do a remove. I'm going to say remove the item at 3. So this is going to be by its index position starting from 0. And if we tried to do this, items.remove 99, there is no value 99, but this is not an error. It'll just return false from this method. So if we say print line items, and we can get the size, print line, curly braces, items.size. And we can also show what the first item is by using the first method. So let's go ahead and run this code. So we can see that we got the first names should be the same because one is using the get method, one is using the index to get it. Then we get 1 and 3. So here is 1, and it goes all the way up to, but not including 3. Here are our immutable list. We added the number 12, and we changed the first item, which was 2, into a 1. There are a total of 9 items. The first item is number 1. And these are some of the things that we can do with lists. Lists can do more than the things that we've shown here, and the Kotlin online documentation has more information on list properties and methods. Sets are collections of unique elements. We create a set using the setOf function. If we initialize a set with 4 3s, we'll find only 1 in the set. That is the superpower of sets. They automatically remove duplicates. So let's create a set, and we'll say val 3s equals set of, and we'll say 3, 3, 3, 3, and we'll print them out. Print line 3s. The different collection types have many of the same methods and properties. Kotlin does this to make it easier for us programmers to make the fullest use of collections. The size property is not only handy, but necessary with sets, since we might not know how many items it holds. So we'll do a print line and say size equals $, and some curly braces, 3s dot size. We can quickly see if a given item is in our set using contains, which returns true if it has it. So we'll say print line, and we'll ask ourselves the question, has a 4, $, and some curly braces, 3s dot contains, and 4. The read-only set isn't as much fun as its mutable cousin, which we create with mutable set of. With it, we can add and remove elements on demand. We'll pass it the numbers 1 to 5. So first we'll give ourselves a little spacing, and then we'll say val fset equals mutable set of, and then we'll go 1, 2, 3, 4, and 5. Typically with sets, we aren't concerned with ordering. However, the default set implementation is the linked hash set, which preserves the order of the set and allows us to access functions based on ordering. Two sets are equal if they contain the same items. Let's create a second set which counts down from 5. So we'll say val bset equals mutable set of, and we'll go 5, 4, 3, 2, and 1. We can use the first method to retrieve the first value put into each set. When we compare them, we'll see that they are not equal. So we do a print line, and we'll just ask the question first equal, and give ourselves a $, some curly braces, fset dot first equal bset dot first. However, ordering of sets isn't relevant to their equivalency. When we check if the sets are equal, they are. And we'll do that right here with a print line. Fset equal bset, and $, fset equal bset. There is another version of the set called the hash set, which doesn't preserve ordering and uses less memory. If we execute the same code but use hash set of instead, we get different results. So let's go ahead and use our good friend cut and paste, and we'll just copy all of this code from right here and put it right below it. Then we'll go ahead and change the names. And now we have an fset2, and we'll change this to hash set of. And we'll do the same things on the next line. This is going to be bset2 and hash set of. Keep that message the same, but we'll change this to fset2, and this to bset2, and this is bset2, and that's bset2, and we should change the question here as well. The sets will still be equal, but their first elements will be identical even though they went into the set in opposite order. In general, you shouldn't worry about ordering with sets. If you need guaranteed order, you probably need a list. We can easily add and remove elements from the mutable version of the set. The add method conveniently returns true if it was able to add the item, false if not. So we'll do a print line and another print line. And inside the print line, we'll ask the question added 6. And we'll say f set.add 6. The remove method deletes the element if it is in the set. If the element is not in the set, it returns false. So we'll do print line and say removed 76, which we know doesn't exist, $ and curly braces, and we'll say fset.remove and 76. Sets are not lists. While they have many of the same functions, there are differences. While both sets and lists have first and last methods, you can't index a set, and it doesn't have the get function. We can convert a set to a list with the toList, and there is a corresponding toSet method for list. So we'll say print line, and we'll say val a list, fset to list. And we'll print out our list. All right, let's run the code. Even though we put 4 3s into our set, there is only 1 remaining since duplicates aren't allowed in sets. We also have a size of 1, and the value 4 is not in our set. The first elements of our mutable sets are different, but since they contain the same elements, they are equal. With our hash set, ordering is not preserved, so our first elements are equal. We were successful at adding a 6, but not at removing a 76. And finally, we converted are set to a list without issues. The Kotlin online documentation has more information about sets than we can cover here. Studying the remaining functions and properties is a great way to master sets. Maps are collections of key-value pairs, and the keys must be unique, but not the values. Creating maps seems a bit weird. We make a pair by joining the key to the value using the word to. The only restriction on the key is that it must be unique. There are no restrictions to its type. We can use integers, doubles, strings, or even classes as keys. We begin with two maps, both of which map integers to strings. So we have M1 and M2. They're identical except one counts up and the other down. Like sets, maps are equal if they contain the same element, and order doesn't matter. So let's go ahead and check to see if these are equal. So we do a print line, and we'll say M1 equal M2, question mark, then a $, curly braces, and we'll just ask the code, does M1 equal M2? We can access the values of a map using either the get function or indexing. Both return null if the key doesn't exist. For most circumstances, prefer indexing. So we'll do a print line, and we'll access and get one of the values. And so we'll say M1 of 2 equals $, curly braces, M1 of 2. However, if you'd like to pass a default value for missing keys, you'll want the get or default function, which returns the passed value if the key is missing. So let's try that out and see how it works. What we'll do is we'll say M1 of 5, and there is no 5, equals, and we'll say $, curly braces, M1 get or default, and we pass it a 5, and we'll also pass it a message not present, and this will be returned if the key is not present. As with other collections, maps have two types, read-only and mutable. We create a mutable map with mutable map of. So let's give ourselves a little bit of spacing. We'll say print line, and we'll say that val cars equal mutable map of, and we'll give ourselves some extra spacing and go to the next line, and we'll say that forward to 1903, comma, GM to 1908, comma, and we'll go to the next line, and we'll say that Dodge to 1913, and finally Tucker to 1944. We can add new elements to the map with the put function, passing the key and value as parameters, but assignment using index is preferred. If the function duplicates a key, the corresponding value gets updated. So now we'll say that cars, and we got the square brackets, and we'll say Tesla equals 2003. Removing an item is painless with the remove function. Pass the key as a parameter, and it deletes the pair if it existed. When successful, it returns the pair's value, or null if the key wasn't present. So we'll say print line, and here we'll remind ourselves, removed Tucker, equal sign, $, curly braces, and cars.remove, and pass it Tucker. We can retrieve all of the keys using the keys property. The result is a mutable set, which is duplicate free. There is a corresponding values property. We can use either of these collections to iterate over items. And so let's just do a for loop, and we'll say for key in cars.keys. And we'll just print the key out, print line and key. We can see if a map contains a given key using the inMembership function. So here we'll say print line and say has Ford, question mark, $. We got some curly braces, and here we have some double quotes, Ford space in cars. That is the in membership function. We can also check to see if a given value is present with the in operator, but we need to use the values property of the map. So here we can say has 1908. We get a $, curly braces, and we say 1908 in cars dot values. And that's because we're checking to see if the value is there. Okay, let's go ahead and run our code. And let's check out the results. We can see that our maps are equal because M1 equals M2 is true. We use indexing to retrieve the value for a key of 2 from M1. And so that is beta. There is no key of 5, and so we got the not present, which is the default message from get or default. We easily remove Tucker from our cars map, and it returns 1944 since it was successfully removed. We use the keys property to iterate over all the keys, including the Tesla key that was added. And finally, we use the in membership function to test to see if we had a Ford as a key. And we also used the in membership function to test to see if we had 1908 as a value. Kotlin keys have many properties and methods. The online documentation is a good resource for what we can't cover here. Kotlin makes it easy to learn collection operations by putting the operations you can perform into 8 groups. When you'd like to manipulate a collection, you first think of which group the operation is in, then determine which function from that group applies. Often the function has the same name across the collection types. Many of the functions take a lambda as a parameter. We haven't covered lambdas yet, so for now, think of them as function shortcuts. The operations are transformation, filtering, ordering, retrieve an element, retrieve a collection, grouping, aggregation, and the plus and minus operators. We begin with a few collections, a list, a set, and a map. Let's begin with transformations. These create a new collection from an older one. The new collection has the same number of items as the old one. The best example of a transformation is the map method. It takes each element from the parent collection, runs it through a lambda, then places it into the new collection. And so we'll create a new collection called TList, and it comes from our list.map, and we'll take IT times 2. And then we'll print it out. Print line transformed list equals $T list. The map function sends the lambda each element in the parent. The IT in the lambda is the element. For the list, we multiply each by 2. Mapping is slightly different for the map. The map supplies the lambda with an entry. So we're going to say val t map equals map.map. Then we create our lambda and we say pair, and we have to go it.key, comma it.value, and we're going to multiply each value by 10, and then we need to end up by converting this back to a map. The map supplies the lambda with an entry, which is an interface that holds the key value pairs. We tweak the value and package the return into a pair. We finish by converting the return, which is a list, back to a map. And let's print those out. And we'll call this transformed map and set it equal to tmap. Filtering operations pass each member of the original collection through a check. Those that pass become a member of the new collection, and those that fail don't. If no members pass the test, we end up with an empty collection. So we'll do a print line to give ourselves a little bit of spacing. And we'll say val f list equals list dot filter. And we'll do an it %2 equals 1. And what we're doing here is filtering for odd numbers. Now we print them out. And we're going to say only odds equals $f list. And let's do one more filter. And we'll say filter f set equals set.filter. And we'll say it greater than 100. And we'll print this one out as well. Only we'll do something slightly different. We'll say is f set empty. And we'll say that it is equal to $ curly braces f set dot is empty. Our other example filters out any numbers less than 100, leaving us with an empty set. We confirm the empty set with the convenient isEmpty function. The most popular way of ordering is to sort. Kotlin has quite a few ways to sort collections. Since the set is already sorted, let's sort it the opposite way using sorted descending. So here we'll just print it out. Sort descending set equals $ curly braces set dot sorted descending. Occasionally, you'll need to reduce your list down to a single item. Before answering filter it, hold up. Filters always return a collection, even if the collection has just one item or is empty. The methods first and last both return a single item. If we use last to look up an element greater than 2, it will return 16 from TList. So we'll give ourselves a little bit of spacing with print line. And then we'll do another print. And in this print, we'll say that TList last colon, and we'll just say, have some curly braces, TList dot last. And then we have a lambda, and it's going to be it greater than 2. And we're missing one curly brace. Converting from a list to a set and vice versa is possible with the conversion functions. We can convert a list to a set with toSet. During the conversion, it removes any duplicates. Converting a set to a list is easy with toList. So we'll do a print line, give ourselves some space, and we'll just convert to an example of conversion. And we'll say list to set equals, and we start off with list dot, and then we do to set. And we do the same thing for set. And we'll say set to list and equals also $, and we say set dot to list. Okay, now let's run our code. Here's our transformed list, which is doubled the original. We've also transformed the map, which has each value multiplied by 10. Next, we filtered the list so only odd numbers remain. And we filtered the set for it so that only numbers greater than 100 would remain, which left us an empty set. And we also sorted our other set descending. And finally here we have TList is last is 16, so this is the last value, which is this 16 right here. And by the way, you can tell it is a single item because Kotlin prints collections surrounded by square braces. So if you look right here, you notice that we got square braces. On the map, we got curly braces surrounding it. And on this list as well, we got square braces. But on the 16, it just printed out the number 16, which tells us it's a single value. And then we also converted list to set and set to list. The standard collection operations simplify learning Kotlin's collections. We only need to learn a few groups and functions, and we can use them across different types. Try to get familiar with the few groups you haven't seen yet. The full list is in the Kotlin online documentation. Sequences are confusing the first time you learn about them, so don't feel bad if it takes a bit for them to make sense. Like collections, sequences are containers. They share many of the same functions, and they are also iterables. Iterables is a fancy word meaning we can iterate over the items in a collection. To understand why we need sequences, we should begin with how collections work. Let's check out the code. We begin by generating the integers 100 to 199. Next, we double every number. Then, we filter out all the numbers divisible by 3. And finally, we return the first number. Let's run this code and see how it works. So now we're going to run it. It doubles all of the numbers. Then it filters all of them before finally returning a single value. And if you think about it, much of the work didn't need to be done. Now, let's do the same bit of code except with a sequence. We can convert a collection to a sequence with the asSequence method. So we'll do .asSequence, and we'll once again run the code. The difference is startling. Instead of having hundreds of lines of output, there are less than 10. A sequence is like a conveyor belt where each value goes through every step of the pipeline before the next one, and the sequence can end on any value. So in this example, a sequence does radically less work than a collection. Before you go full sequence and convert all of your collections, there is more under the hood than shown. For straightforward code like this, collections are usually a better choice. The sweet spot for sequences is when you have vast collections and lots of pipeline functions. We need to talk about one potential weirdness you may encounter. Sequences require a terminal operation to start working. If there isn't one, they won't do anything, no matter how much you say please. So we'll do a print line to give ourselves a little spacing. And we'll say val my threes equals sequence of, and we'll say 1, 3, 5, 7, and 9. Then we'll filter them. And we'll filter them for numbers that are divisible by 3. So we'll say it%3 equals 0. And we'll say print line and my threes equals $ my threes. Now let's go ahead and run this again. Notice the value displayed for my threes. We get this filtering sequence value, which says that the processing for this sequence is unfinished. And interestingly, we can finish or terminate the sequence by appending two lists to the sequence. So if we go back to the code and we instead say print line and my threes dot to list and run the code again, and this time the sequence completes. There are 3 rules for creating a sequence. Use sequence of if you have all of the elements. If you have a collection, convert it with asSequence. And finally, if you have to do something complicated, use a sequence generator. You can find more information about each of these in the Kotlin online documentation. Once again, it is time to show what we know. These challenges help you to think like a Kotlin programmer, so please try this one on your own. For this challenge, we have a list of strings, many of which are duplicates. Use what you know to render the collection without any duplicates. This should take you about 5 minutes. Good luck and have fun. Hi, welcome back. How did you do? The solution is a bit of a trick. Yes, you could use some loops and filters and remove all of the duplicates manually. If you did that and got the code working, I salute you. Goodness knows I've seen plenty of professional programmers do just that, mainly because it was the first thing that came to mind. The trick is remembering two things. Sets don't contain duplicates, and you can convert a list to a set. That's all. So our solution is we convert our list to a set. So we're going to say val set animals equals animals to set. And then we're just going to say print line set animals. Let's go ahead and run this. And you can see that we've got one of everything. If you had a bit of trouble here, please consider reviewing the other sections in this chapter before moving on. Again, while my solution was a bit of a trick, it also illustrates the point that the solution to a problem doesn't have to be complicated. Command line tools are the unsung heroes of software development. Being able to quickly write small apps that perform some mundane but necessary task is a required skill for all programmers. In this section, we'll learn how we can read command line arguments in our code. We'll begin by taking a closer look at our main function. In previous examples, this function didn't have any arguments, but it can. We can pass one argument, conventionally named args, and it must be of data type array of string. All of the arguments are of type string. You'll need to convert them if you expect other data types. It is a little bit tricky to use command line arguments from within IntelliJ. First, we run the project by clicking the green play arrow and click run. Let me go ahead and close this. Click the drop-down arrow of the project selector in the toolbar. So we do the drop-down arrow here, and we click Edit Configurations. In the project list on the left-hand side, we click Our Project. Now we're clicked. Locate the text box labeled Program Arguments right here. On the right-hand side, type a few strings. I'm going to go ahead and enter alpha, beta, gamma, and delta. And click OK to close the dialog box. So now we've closed the dialog box. We can check if args has any values with the any function. So let's go ahead and write some code. We're going to say if args.any. Let's display the first argument using indexing, which we must wrap in curly braces. So we're going to do this here. If we have some arguments, we're going to print line the string equals, and we're going to say $, curly braces, args of 0. And let's just go ahead and run that. And we get string equals alpha. So that's the first of my command line arguments. We, of course, don't have to check for the values one at a time. We can loop over the arguments instead. Using a for loop gives us each of the values in turn and handles things correctly when there are no values. So we say for arg in args. And now we'll just print line each arg out. And we run it. And we see alpha, beta, gamma, delta. Those are all 4 of my command line arguments. And that's all there is to reading arguments from the command line. But our code is suitable only for simple apps where we are only reading in a few strings. Handling complex command lines with flags and options and different data types is challenging. Luckily, there are open source tools to make it easier to do sophisticated parsing. One that I've used is kotlinx.cli. You can find out more about it at its GitHub URL. In this section, we find out how we can get data from the user. A word of caution about user input. Users never do what you expect. Be prepared or your app will crash. The premier way to get input is the readline method. This method takes no parameters and returns either a string or null. So here we have the readline method, and we're just going to go ahead and print out what the user typed in. Notice how we use the safe call operator to get the length. So here's the safe call operator, question mark. We can use the Elvis operator to convert a potential null from readline into an empty string as follows. So we just need to uncomment the Elvis operator, and it's either going to give us a string, and if it's null, it's going to give us an empty string. Then we don't need the safe call operator anymore. By using the Elvis operator, we convert the type from a nullable string to a string. Next, we need to prompt the user. So we're just going to say print, and this time we're just going to say print, not print line. We're going to give ourselves a little bit of space, enter an integer value, colon and a space. Then we're going to say val string 1 equals readline. And then we use the Elvis operator or an empty string. This should be a capital L. We can parse integers and doubles from a readline string. There are two methods we can use to parse a string to an integer, toInt and toInterNull. If toInt doesn't receive a value it can parse, it throws an exception. When toInterNull receives an invalid input, it returns a null. So here we say that val ival and colon int equals string 1 dot to int or null. And then we also give it a question mark colon, that's our Elvis operator, and we're going to give it a 0 this time. So if it sends a null, we'll just take that as a 0, and we're going to print line to print the whole thing out and say you entered colon $sign I value. In my humble opinion, it is better to receive a null you can handle than throw an exception. You could return whatever default value you desired with the Elvis operator. Reading a double is similar, except we replace toInterNull with toDouble or null. So I'm going to use our good friend cut and paste this guy down below. I am going to call this now string 2. This is going to be our double value or D. And we're going to change this to say enter a double value. And we say string 2 to double or null. And then we need to make this 0.0 since it's a double. And finally, we need to change this guy to a double as well. And then we say you entered and D value. Now we'll make a call to the scanner function, scanner, and we'll write some more code in this function. First thing we'll do is we'll print line to give ourselves some breathing room. Then we need to create a scanner object, which we say val scan equals scanner. And this is really important to get right. And we're going to say system dot backtick in backtick. The system.in lets the scanner know to get its input from the default input device, the keyboard. We use the received object to get the input of the desired type. So next, we're going to prompt the user, and we'll do a print, and we say enter an integer, and let's say number. Enter an integer number, colon, space, and then we tell the scanner to return an integer. So we say val num1 equals scan dot next int. We do the same thing for double. Once again, I'm just going to cut and paste this and change all the appropriate variables. Change our text and change this to next double. And finally, we print them both out, and I'll put a little bit of space right there with a print line, and we'll say print line first input number equals $num1, and print line second input number equals $num2. We can read a variety of different types, including our favorites, integer and double. If the scanner doesn't get proper input, it throws an exception, so be cautious with scanner. Let's go ahead and run our program. And it asks us to enter some text, so I'm going to say hello Kotlin. Now it's asking us for an integer value, and I am going to say 42. Then it's asking for a double value, 98.6. Now it's asking us for another integer value, and I am going to say 22, and a double value, 105.1. And it prints out all of the values that we were expecting. Getting input from the users is always tricky. Users can type what you were expecting, something you weren't, and even nothing at all, and your program should be ready for it. My preference is to use the readline function for input, validate the string received like crazy, then convert it into whatever data type I need. Regardless of the technique you implement to get your user input, be sure to test it thoroughly. Once you know how to read and write data to a file, you know most of what you need to know for reading and writing data to any other stream, like the internet or a USB port. In this section, we'll explore a few ways to read and write text files. Kotlin is a pragmatic language that is 100% interchangeable with Java, so it uses Java's file class. We import the Java I/O file package at the top of our app. IDEs like IntelliJ make it challenging to know where your code is executing, making it harder to find files. One trick around this is to put resources in a directory. We've created a folder named resources in the root of the exercise files. We create a variable res that points to this directory. So here we have our res, which points to the resources directory. It only takes a few instructions to read a file. We instantiate a file object by passing it the path to our text file. So here we say val file equals file, and we pass it a string, and the first part of that string is going to be res, and we do a /, and then we say text.text. Then we say file dot for each line print line it. Writing a simple text file is equally effortless. We again create a file object, this time calling the write text method, and we say val write file equals file. We're again going to pass it a string, and we're going to give it res / write dot text. Then we're going to say write file dot write dot text, and we give it what string we'd like it to display. So let's just say Kotlin equals happiness. Often we will want to write an object like a list or a set to a file. We iterate over our collection using for each, calling the file's append text method. We add \n so that each pet is on a separate line. So here we're going to say val p list equals list of, and we're going to say cat, dog, and bird. Then we say p list dot for each, and we're going to say p file dot append text, and the text that we're going to append is a string with a $it and a \n. Each time we call this code, new text appends to the old. We can change this behavior if desired by adding a write text with an empty string. This clears the file before we write to it. And in fact, we do want to do that. So we're going to say pfile.writeText and pass it an empty string. Let's read our pets into memory. We create a mutable list of strings, and we must specify the list data type using angle brackets. So we say val new pets equal mutable list of, and we say string. Then we say pfile dot for each line. We're going to say new pets dot add, and we're going to add it. Then we'll do a print line to give ourselves some space, and we'll do a print line new pets. We use the for each method that we've seen before, only this time we call the add method of our collection. Keep in mind that for each line gives us each line as a string, and our collection is of type string, so it is safe to add them. We've seen how to read and write files using the file objects, but there are a lot more things we can do. We could determine if a file exists by calling the exists method, which returns a Boolean. So we say val exists equals pfile.exists. And we're going to print it out. We give ourselves a little room by doing a \n, and we say pets exist with a question mark, and then do a $sign exists. Then we run our code. Okay, so here is the contents of text.txt, which has 5 items, the strings alpha, beta, gamma, delta, and epsilon, each with a number before it. Here are our pets, cat, dog, and bird. We ask if the pets file exists. It returns to us true. There are many more things that we could do with the file object. I would highly suggest exploring them on your own. The online documentation lists them all. This chapter covered various ways to get data into your programs and also how to write it out. Now it is, once again, time to show what you know. In the resources directory, there is a file, sales.txt, which contains a series of floating point numbers, one on each line. You must read the numbers in and add them to a list of doubles. However, not all the numbers are good. You must filter out any invalid values and then display the list. This challenge should take you about 15 minutes. Have fun and good luck. Hi, and welcome back. How did the challenge go? This challenge was an example of what I like to call straightforward coding. You break the problem into a series of steps, then execute each step. My steps were get a file object to the file, create a mutable list of doubles, iterate over the file's lines, attempt to convert each line into a number, add the non-null values to the list, then render the list. So let's begin. First, we get a pointer to the file. So we're going to say val sales file equals file. We need to pass file object a string. And that string is going to be $res /sales.text. And that is our pointer to the file. Next, we create a mutable list of doubles, and we'll call that sales. And it is a mutable list of, and in this case, it's going to be double. Then we say sales file dot for each line. We say that val, and we'll call this d value, equals it, and this is the current line. And we're going to try to convert it to double by saying to double or null. And we say if d value is not equal to null, then we say sales.add d value. And once we've completed with that, we'll say that sales.forEach, and we actually want a lambda here, and we're going to say print line it. Let's go ahead and run this. There we go. We got all of our values. Nothing's crashed. We've all seen this code before. One thing slightly different is that I am not converting non-null values to 0. The challenge asks that we add valid values to the list. So I only add the value to the list if it is not null. Then I iterate over the list, rendering each value. Keep in mind that no two programmers write code identically. If you are able to complete the challenge, congratulations. If you had some problems, you might wish to review this chapter before moving on. The best way to learn about functions is to create some. Our application needs a function, greeter. We pass it a name, it returns a string with a name appended to a greeting. A function declaration begins with the keyword fun. So we say fun. Then we add the name, greeter, and the parameter list, which is a set of parentheses. It takes one parameter name, which is a string, and it returns a string as well. So we say colon string, and then we do the expression body. We place opening, closing curly braces, and then we're going to do our return, which is going to be a string, and inside of the string, we're going to say hello and $name. We can invoke this function from main by just calling greeter and passing a name. In this case, we'll say Troy. And that's how you create a function. Now, our simple function can be made even more straightforward. We can convert a function that has a single line and returns a value into an expression body. We change the opening curly brace to an equal sign. So this opening curly brace here, we make it an equal sign. We delete the return keyword, and we also delete the closing curly brace. We move everything up onto one line for compactness. Since the string can be inferred, we can delete it, and that is our greeter function, nice and compact. Let's create a new function, volume, that calculates the volume of a rectangular prism. The function takes three integers, length, width, and height, and returns an integer as well. Let's also make it an expression body. So we say fun, volume, and we're going to say length, colon int, comma, width, colon int, and height, colon int. And we're going to say equals, and we just say length times width times height. Now imagine that nearly all the time we call volume, that height is 10. We can see the calls littering our code. We could create a second function that takes only length and width as parameters, and height is a literal value of 10. That would work, but Kotlin offers a better solution, default parameters. We append an equal sign to the height parameter. So we come up here and we say that equals 10. If we pass a value for height, the function uses it. But if we only pass two values, length and width, height becomes 10 automatically. Let's do one more variant of volume. And so this time we're going to say fun volume x. When a default parameter is to the left of a non-default parameter, We can only use the default value by using named arguments. Let's see this in action. We'll make our first parameter, length, the default value. So we're going to say length colon int. And we're going to say that it equals 10. And then width colon int and height colon int. All of this is going to be the same, so let's just copy it. Now, when we call this code, we can say that volume is, and do a $, volume, and we're pass it two values, 10 and 5. And notice that it already knows that it's length and width, and that we don't have one for height because it has a default parameter. And we're going to do a print line and volume again, and say that is $, curly braces, volume x. And now we must use named arguments. So we're going to say that width equals 7 and height equals 13. And those are our named parameters. And let's go ahead and execute this code. And we can see that the volume is 500. And for the second one, the volume is 910. We've covered most of what you need for regular functions. Just remember to use expression body functions only for single line functions that return a value. Lambda functions, also known as lambda expressions or just lambdas by the cool kids, are small bits of code which we can treat like variables. Like variables, we can store them, pass them to functions, and return them from functions. Let's begin by seeing how we declare a lambda. We begin with either the val or var keywords and the name of the lambda. In this case, it's lamb. Next is a colon and the type. Since a lambda is a function, we need to define the types for its parameters and return. We place the parameter types inside parentheses and the return type after an arrow. Next, we define the expression body. We put curly braces after an equal sign, the parentheses, each with its type definition, then an arrow sign, which is a dash and a greater than sign together, and the code defining the body of the lambda. And that's it. Here, we've defined a function to add two numbers. The lambda returns the value of the last expression, which is the value of a plus b. And we can call this lambda by just doing print line and say sum equals, and then we'll do a $, curly braces, lam, and then parentheses, 5, 10. Even though we've defined a perfectly acceptable lambda, you'll rarely see it in this form. Like all things Kotlin, there are shortcuts. We have type definitions on both the variable and in the function. So long as the compiler can infer the types, we don't need both. So we can delete the variable's definitions. And usually the return type can also be inferred. So here is a shorter definition. We say that val, and we'll just call it L, equals open curly brace, a colon int, comma, b colon int. Then we have the arrow, and we say in this case a times b. Once we've defined our lambdas, we can call them like any other function used in parentheses or the seldom used invoked method. So we say print line 5 times 10 equals, and we have a $, curly braces, L, and we say 5, 10. And let's do that one more time, and we'll say 10 times 50 equals $ curly brace L dot invoke. And this time we're going to say 10, 50. Lambda's concise syntax makes them pair perfectly with collections. Here's an even shorter syntax for a lambda. And let's give ourselves a collection. Say list of, and 1, 5, 7, 9, 10, and 13. Then we say print line, and we say num. So we're going to do some work on the num collection, and we're going to call filter. And then we have an open and close curly brace, it less than 7. And that's all there is. Kotlin calls this a trailing lambda. Anytime a lambda is the last parameter passed, we can place it outside of the parentheses. And if the parentheses are empty, we can omit them. Inside of the expression body, when we have a single parameter, we can replace it with the default parameter, it. We can also extend existing classes with Lambda. Imagine we'd like to give the string class an utterly ridiculous greeter method. Here's how it would look. We say val greet, colon, then we say string, dot, open and close parentheses, we give it an arrow, string, and then we say equals, open and close curly braces, and then inside we say what's up, $, this, and a question mark. Once again, we've seen some intriguing things. After we define the variable, we have the class string. Here we inform the world that we are extending the string class. The dot and the empty parentheses let us know there are no parameters for this lambda. The arrow and the string indicates we return a string. Inside the body, we have only a string template with our greeting and the $ this. The this variable is a reference to the object the lambda was invoked on. We can invoke our greeter method on all strings, including literals. So we can invoke it by saying print and line, and then we say give it a literal string, Troy, and then we can say dot and greet. So let's go ahead and run our code. And we see the expected results. We get the 5 plus 10 is 15, 5 times 10 is 50, 500, 1 and 5. These are all the numbers that are less than 7. And we get our completely silly greeting, what's up, Troy? Understanding lambdas is a key to making your own code more idiomatic Kotlin. Be sure to take the time to play with lambdas on your own. An anonymous function is a function with no name. Its definition is identical to a regular function, except for the missing name. Like a regular function, we can define it with either an expression or block body. We can use anonymous functions instead of lambdas with collections. Admittedly, lambdas are a better choice. So here we have a list called num, and we're going to say fnum equals num.filter. And we're going to create ourselves an anonymous function. So this function, and it's going to take an a, which is an int type. It's going to return a Boolean. And inside of it, we're going to say return a less than 7. And then we'll do a print line and print fnum. Like so many things Kotlin, we can shorten anonymous functions too, just not to the same degree as lambdas. We can rely on inference and remove the parameter and return types. By converting to an expression body, we can remove the curly braces. While this is shorter, we can't remove the keyword fun or the parentheses even when they are empty. So if code brevity is a contest, the lambdas win. So we'll create another filtered list, and we'll call this fnum2. And once again, we are operating over our list called num, and we're going to say filter and fun, and we'll call this guy a, and say that it equals a less than 7. And once again, we'll print it out, and this time it's fnum2. One place where anonymous functions beat lambdas is for those rare occasions when we need to have multiple returns in a lambda. So we'll do a print line to give ourselves a little room. And we say val get age, and we'll call it get age 2 equals, and we have to say lambda @. Then we have opening curly brace. Then we have age :int, and we have our arrow. Then we say that if age is greater than or equal to 65, then we're going to return, and this is at lambda, that this person gets the senior discount. Next we say else if age is greater than or equal to 21, then we do a return, and this person pays the regular price. And finally we say if none of those are true, we just say underage. And then to invoke this, we're going to do a print line. Client pays, and then we say $, open curly brace, get age 2, and let's see, pass it to number 32, and a space and price. Now that's how we would do this with a lambda, and now let's contrast it with an anonymous function, and we'll use our good friend cut and paste again. And this is just going to be get age, and we go ahead and replace this with a function, and the function's going to take in age, which is an integer, and then we say colon, it returns a string. We have the opening curly brace, don't need this right here. We say if age, and then we just do a return. And likewise right here, we do a return. And finally, if none of those are true, we do a return. And we say that client, and we call get age. And let's make them 70 years old. So with anonymous functions, we can return as much as we like, and there's no need to put labels anywhere. So let's go ahead and run this code. Okay, we can see both the regular and shortened anonymous functions produce the same results, and we get similar results from using a lambda or an anonymous function for multiple returns. So with the anonymous functions, we must be more explicit. If we need to return a value, we must use the return keyword. If an anonymous function lacks a return, it returns the default unit type. If there's disagreement between either the variable's type or the function's return type, then it is a compilation error. So prefer anonymous functions only when there is more than one return in the function. The multiple return mechanism in lambdas is a bit clumsy. The use of anonymous functions is rare, but occasionally we need them. Lambdas are the preferred workhorses when we need bits of code. A local function is one that resides within another function. It has access to all of the local variables of the outer function and is uncallable outside of the outer function. Why do we need local functions? They are an alternative to littering your code with functions called only by one other function, or worse, having all including mega functions. Local functions can also be an alternative to creating a class, which may be overkill for a small need. Perhaps an example might explain things better. We have a function named isPalindrome. It takes a string and returns a Boolean indicating whether or not the passed string is a palindrome. A palindrome is a word that reads the same way forward or backward. One example is the word level. There are many ways to write this function, but I like this one because it breaks the logic into discrete steps. We must declare local functions before use, so we declare ours. Do char's match first. We'll come back to the function's body in a minute. Let's continue with the rest of the code of the outer function. We make a quick check to see if the passed string is empty or only one character long, either of which we'll consider a palindrome. Then we call do char's match with the index of the initial front and back characters. From within inside of do chars match, if front is greater than back, we've passed the halfway point and the word is a palindrome. Next, we do a case-insensitive compare of the characters and see one of the ways that local functions are fantastic. The variable words is a parameter in the outer scope, but we have access to it. Local functions allow us to create something like lightweight static classes. If our characters at the front and back of the string don't match, we return false from the inner function, which returns false from the outer. The final line of the local function does a recursive call to do chars match with front and back indexes increased and decreased by 1 respectively. We can test is palindrome by iterating over our word list. So here we're going to take our list of words. We're going to say for word in words and do a print line and say palindrome, $word, question mark, and then finally we're going to call is palindrome with the word. Now let's run the code. And we see that the word race car is in palindrome, civic is 1, level is 1, but butter is not. Local functions are not exclusive to Kotlin. Other languages have them as well, although the name might be different. In C#, for instance, they're called inner functions. Local functions are perfect for code that nothing outside the function needs. We've learned a lot about functions in this chapter. Now, let's put some of that new knowledge to use. Everything in Kotlin is an object, including functions. In this challenge, we've written a function named replicate. The function accepts as its sole parameter a function which we must pass to it. Read the function's definition, then create a function that matches the definition. The function should print message to a line once for each value of count. So if count is 5, we should see message displayed on 5 lines. Then pass the function to replicate. Feel free to use any function type that you like. Please try this challenge on your own before looking at the solution. The challenge should take about 10 or 15 minutes, but take as much time as you need. Welcome back. Hopefully the challenge went well for you. I generally like to solve puzzles like this challenge step by step. The first step is to determine what kind of function we should pass to replicate. The function signature tells us that we need to send a function that expects an integer as the first parameter and a string for the second. The unit return type tells us the function doesn't return anything. I decided to pass a lambda to replicate, since the function is the last parameter. So we're going to make a call to replicate. And since the function is the last parameter, I can pass the lambda in trailing format, which is outside of the parentheses. Here's where our lambda is going to go. And since there's no other variables, I can omit the parentheses when calling replicate. So I don't even need to call it with anything. The replicate lambda begins with 2 parameters, which I've named count and message. So count, comma, message. Then we have our arrow. You can choose whatever names make you happy. Then we print message count times. There are plenty of ways to loop the message out. We're using a for loop to print out the message. So we're going to say for, and we'll call this index in 1 ... count. And this is a range. Then we do a print line message. Please note that we are counting from 1 instead of 0. And that's all there is to this challenge. So let's go ahead and run it. And we can see be cool printed 3 times. And just for giggles, let's go ahead and change that to say 5. Run the code again. And we see be cool printed 5 times. Hopefully you came up with something similar. Remember that no two programmers are going to come up with the same solution. In object-oriented languages like Kotlin, classes are the primary way that we create data types. The definition begins with the keyword class, the name follows, and it finishes with a pair of curly braces. So let's create our own, and then we're going to call it class. And there's our class definition. Classes are public by default. We change their visibility by adding private, protected, internal, or the redundant public before the class keyword. We can apply visibility modifiers to the class's constructors, properties, and member functions. With each of them, the default is also public. In Kotlin, we only specify a visibility modifier if it isn't public. We can create a class with an even shorter definition, but its usefulness is dubious. Just the keyword class and a name creates a perfectly legal class. So we can call this one class short class, and that's it. We use a class's constructor to pass data from the outside world into it. Kotlin has two kinds of class constructors, creatively named primary and secondary. We define the primary constructor in the class header after its name with the keyword constructor and a list of names and types wrapped in parentheses. It kind of looks like a function's parameter list. So class with constructor, and we say name, colon string, and age, colon int, and some curly braces. There is, of course, a shorter version since the constructor keyword is usually not mandatory. So we can say, call this one without constructor, and even though it does have a constructor, we can get rid of the constructor keyword. Only when the constructor has an annotation or visibility modifier is the keyword constructor mandatory. If you'd like to make the primary constructor callable only to code available internally in the same file, we add the internal visibility modifier to it, which makes the keyword constructor necessary. And so here, what we're going to do is do a little bit more cutting and pasting, and we're going to call this mandatory constructor. And what we're going to tell it is that we are going to make this one internal. And if we try to delete the word constructor now, we get a message telling us use constructor keyword after modifiers of the primary constructor. So it is mandatory now. The parameters in the primary constructor are not visible to code outside of the class. However, we can use them to create class properties. So we have class, course, property, and its course title, which is of string type, and the name of our property is title. We're going to set it equal to course title. There is a shortcut available with properties. If the class's parameters are identical to the properties it needs, we can cut out the middleman. Every parameter that we'd like as a property, we add either the val or var keywords. And we don't have to make all of the parameters into properties. We can be choosy. Some parameters can double as properties, and some properties can be immutable. So we have a class person, and we're going to make this a property, first name, and it's a string type. And we're going to have another parameter, last name, and this one will not be a property. And we'll have another property, which is going to be age, and this one is mutable, and it's going to be of type int. We can have a custom getter, setter, or both. So here we have a class, and we're going to call this one course, and it will have a course title, which will be a string type, And then we're going to say private val title equals course title. And we're going to have an internal variable description. And we're going to initially set it to an empty string, but it is going to have a getter. And that getter is going to do a return. And we're going to check to see a field. And field refers to description. And that's what we call it internally. And if field is null or blank, then we return no description. Else, we return $ field, and we put an exclamation point. And I need to move this parentheses. Should have been here. Member functions give us a way to change the behavior of a class. They are like other functions except they live within the class and have access to its internals. Let's create a show function to display our course title. So back inside of here, go to the end of the class, and we're going to say fun show with no parameters, open and close parentheses, and we're going to do a print line title. Like other objects, we can print an instantiation of a class. The toString controls what the class displays. The default implementation is not very useful. Luckily, we can override its behavior with our own. So back inside the class, we're going to say override fun and toString. And our implementation for this is going to be a string template with a $, title, a dash, and then a $ description. Okay, so now let's call some of this, and we'll say val course equals course, and we're going to call this Kotlin essential training. And once we have course, we're going to say that course dot description equals secrets you want to know. And then we'll do a course dot show, and we'll do a print line, and we'll just print out course. Okay, let's run our code. And first thing we do is we get a course.show, which is going to show our course's title, which is Kotlin Essential Training. And then we're going to do a course print line, which is using the toString override, and it's going to print our title and our description. Now, if we comment out our toString method and run this code again, you notice that our toString is not very helpful. It just gives us a definition of a class. We covered a lot about classes. We've seen how to create them, send them parameters, and how to make those parameters properties. And finally, we learned how to add behavior to a class with functions and change their renderings with toString. Classes are the main component of object-oriented programming and Kotlin. You need to master classes to master Kotlin. We define default class parameters the same way we define them in functions. We add an equal sign and a value after the definition of a parameter to give it a default. Any parameter with a default is optional when we instantiate the class. If we include a value for it, we override the default. So here we have state, and we have given state a default value of CA. And in our main, we're going to say val car equals vehicle, and our vehicle definition is going to be Chevrolet and a Volt and 2018. And we don't need to give it a state because it will use California for the default. And we'll do a print line car. It should not be a surprise, but we can also use name parameters with classes. Using the parameter's name makes it clear which one you are referencing. It especially helps when you have 3 or 4 strings in a row and you like to be sure which is which. So once again, we're going to say val, and this is going to be car number 2, and it is a vehicle. And this time, we're going to say that state equals NV, year equals 2019, make equals Ford, and model equals Mustang. And we'll do a print line for it as well. We can initialize our properties by assigning parameters to them. If we need to perform more complicated initializations, we need to use an init block. We can create as many init blocks as we need, and they execute in their definition order. So back inside our class, we're going to say init. And inside of the init, we're just going to do a print line, first initializer block, and do a $sign this. When init blocks, default parameters, and property assignment isn't enough, we can create one or more secondary constructors. Its name has nothing to do with how many constructors are in the class. It is all about location. If it is within the body of the class, it is a secondary constructor. The secondary constructor must call the primary if it exists. We reference the primary by adding a colon, the word this, followed by parentheses. We wrap any parameters we are passing to the primary in parentheses. So now we're going to create our secondary constructor. We use the name constructor. We have an open parentheses. And in this case, we're going to make this multiple lines. We're going to have a make colon string, a model colon string. Let's go down a line, a year, which is an int, a state, which is a string. And in this case, the thing that we're adding to the secondary constructor is going to be a style, which is a string. Then we close this up. Now we must call the primary constructor. So we say that this, and we pass all the things to it that it needs. So it needs a make, a model, a year, and a state. And then as far as the style is concerned, we're going to handle that one within the secondary constructor. And so we'll say this dot style equals style. And right here, we'll create a private var style. Now it's var because we can change it. And right now, we'll just make it empty. And then within our main function, we'll create a third car. And this is going to be car 3 equals vehicle. And we're going to call this one Tesla Model S 2019. The state is going to be RI. And the style is going to be P100D. There is no limit to secondary constructors. You may make as many as makes you happy. They execute one by one in order, and each must call the primary. All right, so we're going to create one more secondary constructor. And so we'll first make a copy of the first one, and we'll put a comma. And we're going to have one more thing called status, which is going to be a string. And then here, we're going to pass the style. And finally, we're going to set status equal to status. And this again is going to be private var status. And it's going to start off as an empty string. Okay, so then inside we're going to create one last car, and this is going to be car number 4, and it is a vehicle again. Our make is going to be Tesla. Our model is 3. Our year is 2019. We're going to use California for the state. Our style, and let's go down to the next line. Our style is going to be performance. And our status is going to be new. And let's go ahead and print this car. That's car number 4. And let's go ahead, because we didn't print out car number 3, so print car 3. Now, let's go ahead and run this code. And we can see each one of these first initializer blocks, that is coming from our init block. And we get each of the cars in order. We get our Volt, our Mustang, our Model S, and our Model 3. So we see what we expected. We learned that classes and functions have a lot in common, but that shouldn't be too big of a surprise. We also learned how to create init blocks and secondary constructors. Okay, that's enough about constructors. Let's move on. Creating classes can be rather grunty work. Often you find yourself writing the same lines of code with minor changes over and over again. This repetition happens a lot with a specific kind of class, called the DTO, or data transfer object. We use DTOs to move data into and out of our programs. One of Kotlin's design goals is to be concise and eliminate boilerplate wherever it can, so we have the data class. Data classes are wonderfully beautiful things. Let's see why with a few examples. As an example of a data transfer object, we'll have a student class. Our class only needs 3 properties, first and last name and the grade level. Voila, that is it. Let's print out one of our students. So we just say students, sub-0, and then we run the program. Oops. You probably saw where I was going there. No big deal. We need to override the toString method. So we come back into this class, get in between the curly braces, say override, select toString, and then we just need to change the template here. So we put in a string, and we're going to have open and closing parentheses. Inside of the parentheses, $ first name, space, $ last name, space, and $ grade. Okay, let's run the code again. Okay, that looks pretty nice. We get the first and last name and the grade level. We realize that 2 of our students are identical, student 0 and student 1. It would be nice if later we could check for duplicates. Let's see if we can detect if 2 instances of our class are identical. We add a single line of code to print the objects and check if they are identical. So here we go, print line, and we're going to say does, and it is $ curly braces, students, sub-0, and then equal, $ curly braces, students, sub-1, then a colon, and then we're just going to actually compare them. So $ curly braces, students, sub-0, equal, students, sub-1. All right, so we go ahead and run the code. And darn, according to Kotlin, the objects are not identical. Kotlin only thinks 2 objects are identical if they both reference the same memory location. However, we can override another method, equals, so we can tell Kotlin how to compare our objects. So let's go back into our class again. Let's do another override. And this time we want the equals method. And for the equals method, I'm going to go ahead and delete this highlighted line. And we're going to say if other is student. Now, other is a reference to the other student class. And so by saying is student, we're checking to see if it is a student object. Otherwise, we're just going to say return false, that the objects can't be equal because they're not even of the same type. Then we have a return, and we have last name equal other dot last name double ampersands first name equal other dot first name double ampersands. And finally, we have grade equal other dot grade. Okay, so let's try our class again. We run it, and we see that AbelBaker11 equals AbelBaker11 is true. So we've done that. But we also notice that suddenly our class is lit up. And so let's see what IntelliJ has to say. And it says class has equals defined, but does not define hash code. So normally these two methods go together. And luckily, IntelliJ can generate this method for us. So let's have IntelliJ generate the hash code method for us. We want it to compare all of our properties, and we say OK. And it comes up with a way of generating the hash code for us. And let's just run the code to make sure nothing broke. And we see the same output as before, so we're looking good. Now, often students have siblings. It would be nice if we could copy the information from an existing student to the new one and change only the properties that are different. Unfortunately, we don't have a way to do that. Rather than continuing down this path of increasingly grunty work, let's see an alternate way, the data class. So we're going to come up here. We're going to make a copy of the first line of this class. We're going to comment this entire class out. And right here, just above the main method, we're going to insert a class. And right in front of it, we're going to say data class. And we don't need the curly braces at all. Let's run the code to make sure that nothing broke. So we get a student printed out, and we also get the comparison, and it went off the edge here, but it says true. Now, let's say that our student Abel Baker has a sister whose name is Charlie, and she's an identical twin. We can make a copy. We can say val Charlie equals students sub0 dot copy, and we only want to change the first name, so first name equals Charlie. And let's go ahead and add that to our students. Students dot add Charlie, and then let's go ahead and print out all of our students. So for student and students, print line student. And let's run this. All right, so we didn't break anything that we had gotten working previously. We can see here are the original 3 students, and we also now have a Charlie as a student, and the name, last names are the same, grade levels are the same as our first student. Hopefully, you see why data classes are so cool. They help you eliminate dirty coding that you most likely didn't want to write. Okay, let's cheer together. Composition over inheritance. I know that nearly every book on object-oriented programming tells a different story. They talk about inheritance as though it is the greatest thing ever. The books are full of examples of animal being the superclass of mammal and mammal the superclass of cat ad infinitum. And it seems beautiful because you understand it. It makes sense, and suddenly programming seems easy. Now I'm here to burst your bubble and to tell you the truth. You don't need inheritance, and you don't want it. I know these are big words, but hang in there. I'm going to back them up. We are going to use the file composition.txt, included with the exercise files. It has all of the code for each step as we walk through the explanation. Now, let's pretend we are making a payroll system. We need a way to track hours that employees work and pay them based on their hourly rate. We begin with a person class, a favorite of the inheritance crowd. A person has a first name and a social security number. All right, so we go ahead and cut and paste our person class. Next up is our employee class. It inherits from the person class and adds a job title and an hourly rate. We must make the person class inheritable. We make it abstract since we never instantiate it, and add an abstract getName function. But if inheritance is so great, why didn't the Kotlin designers make it the default? Let's forge forward. So here in our employee class, we inherit from person, and we keep track of total hours. We have an override for getName. We have a way to track hours, and we have a way to do some work. In our main class, and let's go ahead and put this on multiple lines. We have our first name, our social security number, our job title, and our hourly rate. And we're going to have them print out, hey, what their name is, and do some work. So let's go ahead and run this. And we get my name is Abel doing bit wrangler work. Okay, we're feeling pretty good about ourselves. Then we realize we missed something. We forgot about salaried employees. We decide to create a salary class as a child of employee. For the hourly rate, we pass 0. That serves as a signal for the employee class not to process the pay. The salary class handles it. So let's go ahead and get our next copy. And this is now step 3. And we're going to change our employee class and our main function. So we have our employee class, and we have our salary class, which inherits from employee. Notice that we are passing hourly rate of 0, 0. And let's go ahead and execute this code. And we get, hey, my name is Abel, doing bit wrangler work. My name is Beth, doing program manager work. So we're looking pretty good. Please hold off your shrugs of indignation. I know this is a hack, but over my years in the trenches, I've seen worse. Now, every object of the salary class has baggage from the employee class it doesn't use. Extra code is one of the problems with inheritance. Classes get stuck with everything they inherit, including stuff they neither want or need. Now we get a new requirement. There is a concern that we are overworking the rescue dogs. It should be easy to track their hours in the system like other workers, right? Now we're stuck because a dog isn't a person and it doesn't get paid. We've discovered another inheritance flaw. Inheritance creates types based on what they are. Let's rewrite our app using composition. So now we go back to composition.txt file. This is going to be step number 4, and this is going to replace everything. And so we go back to the top of the file, just below where it says package, all the way down to below main, and we're going to paste in what we just got and take a look at it. With composition, we design our types based on what they do, not what they are. So we create 3 interfaces. The first, I worker, does work. The second, I being, exists and has a name. The final interface, I payment, determines their pay. We create 3 classes that implement the interface and make a class employee which requires implementation of each interface. So all the way down here, we have employee, and it needs a worker, something that upholds to the worker interface, a being interface, and a pay interface. Now, first off, let's make sure that we can do everything that we were doing before. So we run the code, and we get my name is Abel, doing bit wrangler work. My name is Beth, doing program manager work. So our code does what the previous implementation did, plus it is trivial to add the rescue dogs. And now this goes to step 5. In fact, I'm going to do this in 2 parts. I'm going to copy the no pay class over, and I'm going to copy the rescue dog implementation. All right, so we have a class, no pay, which adheres to the iPayment interface, and it just says, hey, you get 0.0 as your pay. Now for our rescue dog, we just say, hey, it's a worker. Its job title is rescue dog. Its being, its name is Fido, and its pay type is it gets no pay. Put all of these on separate lines so they're a little easier to read. Being and also being. And let's run the code again. And everything's still working. We get my name is Abel, doing bit wrangler work. My name is Beth, doing program manager work. And my name is Fido, doing rescue dog work. Implementing composition requires a bit more planning up front, and initially it is more code. So there's definitely more code here, but notice how small our classes are. Each of the classes that implements one of the interfaces is much smaller than one that does everything. By focusing on what our types do rather than what they are, we can write much smaller classes that don't need inheritance. A companion object is an object declared within a class and marked with the companion keyword. The companion and all of its functions and properties are accessible via the class name, assuming they are publicly accessible. Why would you want a companion object? Here are a few reasons. I am sure there are more. To scope properties and functions to a top-level scope, but avoid polluting the global namespace. To provide static constants. And to supply a class with a factory method. Let's add a companion object to a class. Then we'll add a factory method and make it the only way to create copies of the class. Making a companion object is straightforward. Pick a spot in the class and add companion object along with opening and closing curly braces. So we'll just come down here towards the bottom. We'll say companion object, open and close curly braces, and we'll open them up. A class can only contain one companion object. Attempting to add another is a compile time error. The companion is accessible via the class's name, unlike ordinary objects which require their name in the scope chain to access their innards. If you name a companion, you can optionally include that name in the scope chain. By the way, you can apply visibility modifiers such as private to a companion object. Of course, making it private makes it inaccessible from outside of the class. Now that we have a companion object, let's make it so we can't instantiate our class directly. We're going to come up here just before the word constructor, we're going to type the word private. Now, if down here inside of our main method, if we say val c1 equals can't create, and if we try to create, we notice that we're getting errors. And if we hover over one of the errors, it says cannot access init. It is private and can't create. So let's just comment that out for now. And then inside of our companion object, we can use factory methods to create objects even though we can't directly instantiate the class. And so we're going to say fun factory, and to the factory method, we're going to pass a message, which is a string. We are going to return an instance of the can't create class. And inside of our factory method, we're going to return can't create and pass it message. Now, back down in our main method, let's uncomment this block of code. And instead of trying to instantiate can't create directly, we're going to say dot factory. And then we're going to do a c1 dot show. Companion and other objects don't have access to an instance of the class unless a reference is passed in. As an example, if we wanted to print the class's message property from the companion, we would need to pass a reference to the instance. Doing so doesn't make much sense, but you could if you wanted. Let's make a print function. So back inside of the companion class, we're going to create a function. We're going to name it silly print. It's going to take self, which is an object of the can't create class. It's not going to return anything. It is just going to do a print line. And in the print line, we're going to say a message accessing, and then $, curly braces, self, contact.message. Then inside of our main method, we're going to call can't create .sillyprint and pass it C1 and execute the code. And we can see that we get hello there being printed from show message and accessing hello there being printed from our companion class. The companion object is a convenient place to store constants related to the class. If we needed to know the speed of light in meters per second, we could store it. So inside the companion object, we're going to say const val light speed equals 299 underscore 792 underscore 458. And then if we needed to print that out, we could say print line, the speed of light is $, curly braces, can't create dot light speed, and then do a space and meters per second. Now we can run the code. And we see hello there, accessing hello there, and the speed of light. And there it is in meters per second. Kotlin's companion object is roughly equivalent to a static class in other languages. In this section, we took a quick look at them and explored some possible usages, including my favorite, a convenient place to store class constants. It's time again for us to show what we know. We have created a class named Bosco. We want to keep track of the number of instances that get created. When the program begins, there should be 0. Each time we instantiate Bosco, the count should increase by 1. We aren't concerned about what happens if objects go out of scope. We only want to know how many instances of our Bosco class got instantiated. Your implementation must include a show method that shows the number of instances created. Please uncomment the line bosco.show in the main function and test your class implementation against the provided code. This challenge should take about 10 minutes. Good luck, and please try to solve it on your own before looking at the solution. Welcome back, and how did it go? Hopefully you solved the challenge. Let's check out one solution. Don't worry if yours is different. Since we need to keep track of information that lives outside of a single class, we add a companion object to Bosco. It doesn't need a name, so we don't give it one. It does have a single private variable, count, which we initially set to 0. So we come up inside of the Bosco class. We say companion object, open and closing curly braces, and we have a private var count equals 0. We add two functions to the companion object, increment and show. The latter, show, allows us to see how many classes we created. The first method, increment, is the heart of our solution. We call it every time we create an instance of the class. So just below count, we say fun, increment, doesn't take any parameters and it doesn't return any parameters, and we just say count plus plus. Then below that we say fun show, doesn't take anything, it just does a print line and say $count instances created. To call the increment function, we add an init block to the Bosco class. The code in the init block executes every time we create a new Bosco. So we say init, open and close curly braces, and we call increment. Now we come back down here, we uncomment the bosco.show, and let's run the code. And we get 4 instances created, which is the correct answer. If this was too much of a challenge for you, you might want to go back and review some of the previous videos in this section. There is an old joke we used to tell each other at a startup I worked at many years ago, which I think is still funny today. Don't put bugs in your code, because you'll only have to take them out later. Bugs happen, even to the best of us, so all of us should have a strategy for dealing with them. Luckily, IntelliJ has an excellent debugger. Let's learn how to use it. The name debugger is a bit of a misnomer, since it doesn't remove bugs from your code. What it does is give us a way to examine our code while it is running and hopefully find errant code. It does this by allowing us to place breakpoints in our code. A breakpoint is a place where execution stops. There are two kinds of breakpoints: unconditional and conditional. We set unconditional breakpoints by clicking in the gutter between the line numbers and the editor text. Breakpoints are toggles. Clicking once on a code line sets it, twice removes it, and so on. Let's set a breakpoint on line 12. So we come over here, line 12, in between the line numbers and the editor text. We click once, a red breakpoint appears. Click twice, it disappears, and then once more to set it. Now we come up here to the play arrow and click debug. We type a few names in: alpha, beta, and gamma, and then we hit return and then empty, and then our code stops on line 12. The execution stops at our breakpoint. The current code line is highlighted and our breakpoint has a check mark in it. The top row of the debugging window holds a toolbar of icons. We have show execution point. Clicking this takes us to where the debugger stopped. Step over executes the code without stopping, one line at a time. Then we have step into, which goes into the current function. Step out of, which goes into the code we didn't write, decompiling it if necessary. Step out of exits the current function. Drop frame falls back to the previous stack frame. Don't worry too much about this one. It is a little bit complicated. Run to cursor, and this runs the code from the current execution point to where the cursor in the code editor currently is. And then we have this thing that looks like a little calculator, which is called the evaluate expression. It brings up a code calculator so you can real-time evaluate Kotlin code. Along the sidebar are more icons. We have rerun, resume, pause, stop debugging, view breakpoints, and then mute all breakpoints. And what this does is once you click it, all of your breakpoints are still present, but they're not going to stop until you unmute them. Clicking step over executes one line of code at a time. Click on line 17. So we're going to put our text cursor on line 17. Then we click run to cursor. So here's run to cursor. We click it, and then it executes all the code up to where the cursor is now. This line has not executed yet. If we look at the console, we can see that we have our message. We have 3 names. We print the names, but it has not printed enter first integer yet. And we go back to the debugger. We can set conditional breakpoints by clicking in the gutter, then right or control clicking the breakpoint. So let's go all the way up to line 8. We're going to click, and that gives us a breakpoint. Then we're going to right click on it and click the more link, and this brings up the breakpoints window. Then we're going to click on condition, and we're going to say input dot starts with and a string a, and say done right here. Then we're going to hit rerun to start the debugger all the way back at the beginning, and we'll type a few names. Now we're looking for a name that starts with A. So I am going to say beta, gamma, delta, and now I say alpha, and we stop. That's a conditional breakpoint. Our text editor is highlighted. Our breakpoint has a check mark, and it has a question mark, showing that it's the conditional that triggered. Another conditional breakpoint is pass count. This is particularly useful when you have a loop that's going through and you don't necessarily want the code to stop the first time through or the second time, but some number of times. So let's go back in here, and we're going to say more. We're going to uncheck condition. We're going to check pass count, and we're going to say 2 and say done. And then we'll do a rerun again. And so the first time we'll say alpha. The second time we'll say beta. And it stops on the second time because we gave it a pass count of 2. Sometimes we want execution to stop once, then we would like the breakpoint to disappear. For those occasions, there is remove once hit. So once again, we'll come in here, we'll right click it, we'll click the more, we'll uncheck the pass count and check remove once hit and say done. We'll rerun everything again and we'll say alpha, beta, and now we get our breakpoint. We say resume, and notice the breakpoint disappeared on its own. Conditional breakpoints are straightforward to understand. Take a little time to explore them before you need them. In the dark days before the introduction of IDEs with fancy debuggers, there was the print statement. Its name may not have been print, but it was a way to write some text out to a screen or printer. This text let us know how far our code got and what its state is. For this reason, I like to think of the print statement as the original debugger. Modern debuggers still let us know how far the code has gotten and what its state is. The primary way to watch variables is via the Variables tab of the debugger. When execution stops, this tab shows us the current value of every in-scope variable, scrolling text when necessary. We can also edit the value of variables, including some immutable ones. Let's set a breakpoint on line 19. We will click to play, click debug, enter some names, enter an integer. We'll enter 1001. And now we've hit our breakpoint and we can see the string 1001. If we right click it and say set value, we can edit this string, and keep in mind, you shouldn't change the type of the data, but you can change whatever the data is as long as you remain in its type. So in this case, we are going to change this to be 20,002 and hit enter, and then tell it to continue, resume running. Go back to the console, put in the second number, and we'll just say 2. And you can see there's our 2002 that we entered. We can also compare the current value of a variable with a value stored in our operating system's clipboard. This comparison can be handy when you need to compare long passages of generated text for a small change. The debugger lets us keep an exceptionally watchful eye on some variables by placing them into our watch list. If you don't see the Watches tab next to the Variables tab, try clicking on the eyeglass icon. So let's bring up the debugger again, and we will start debugging. We'll only enter one name this time. We will enter a number, and we have the Watches tab right here. But if I click on this eyeglass icon, the Watches tab disappears and the eyeglass icon appears right here, and I can make the Watches tab appear again. Now let's bring it back up, and I will hover over and right click and then add 2 watches. So now we can see string 2 is here, and I'll also do the same thing for integer 2, add 2 watches. Now it appears over here. An unresolved reference just means that the code hasn't encountered this variable yet, so it doesn't have a value. And we will resume execution. Put a breakpoint right here before the program ends. Go to the console and enter our second digit, and we'll make it 200. Now, let's go back to the debugger. We can see that string 2 equals 0, 0, integer equals 0. And that's because there was something screwy with the console. But those are our watches. Here are our variables. We can delete any of these watches by highlighting it and clicking the minus button, or I can right click within the Watches tab and remove all of the watches, or I can add a new watch, or I can just remove a single watch. Let's just go ahead and remove them all. And that got rid of all of the watches. Keep in mind that debugging isn't free. Your code runs a lot slower under the debugger. Often the performance impact doesn't matter, but high performance code may become unusable. The debugger has more features we haven't mentioned. All of the icons identify themselves when you hover over them. Some also display longer explanatory text in the lower left corner of the editor. Hover over the Run to Cursor. So when I hover over Run to Cursor, down in the lower left corner, which is really hard to see, it says Run to the line where the caret is. Do take the time to get to know the debugger better. Coroutines are lightweight threads that help us write fluid applications. One thing coroutines do is help us to run code asynchronously. The best way to handle tasks like internet calls, file access, and database queries is to run them asynchronously. Coroutines are not part of Kotlin's core. They are a library. So before we can play with coroutines, we need to import kotlinx.coroutines. Depending on your setup, you may also need to add them to Gradle or Maven. It helps if we understand the difference between synchronous and asynchronous code. Synchronous code is like going to a grocery store with only one lane open. Everyone must wait their turn. If the checker spends 1 minute with each customer and there are 3 ahead of you, you won't leave the store for 4 minutes. We begin with the function longcalc. Pass it a number, it adds 1 to it and returns the results. It has a built-in 1-second delay to simulate a long calculation. The function has the keyword suspend, making it callable from coroutines. We create a method synchronous. So right below longcalc, we're going to say fun synchronous. It doesn't take any parameters, but we're going to make this an expression body and make a call to run blocking. Suspend functions are callable only from coroutines, so we wrap the code with run blocking, which makes it a coroutine. From our synchronous method, we call longcalc 3 times, passing different values with each call, and we store the results in variables. So we're going to say that val x1 equals longcalc, and we're going to call it with 100. Then we're going to make 2 more copies of this, and we're going to rename these variables. One's going to be x2, the other x3, and we'll change the values so that we're calling it with 200 and 300. We create a list of the variables and add them together with the sum method. So we're going to say that val sum equals list of x1, x2, x3, and then we're going to do a dot sum to add them together. And finally, we'll do a print line and say that results equal $sum. Now, from our main method, we're going to wrap the call in measured time millis. And what this does is it returns the time that it took to execute the code in milliseconds. So right here, we're going to call synchronous, and we're going to run the code. And we get the results of 603, and that it took just slightly over 3,000 milliseconds, or 3 seconds. Async await is like a grocery store with lots of open lanes. Each checker still takes a minute to process a customer, but the store can process many customers simultaneously. The calls to longcalc don't need to run sequentially. We only need to get the results from each and add them. So, like a grocery store, we can open more lanes. Let's make a copy of our synchronous function and name it async await. So let's give ourselves a little bit more room. We'll copy this. We're going to rename it async await. It doesn't take much to make our code asynchronous. We wrap each call to longcalc in a separate async block, allowing the calls to happen at the same time. So just before the word longcalc, we're going to say async, an open curly brace, and then close the line with a closing curly brace. And we're going to do that for each of these calls to longcalc. Async converts the values from integers to deferred objects. We can still create a list with them, but we must wait for all the deferred objects to resolve with await all before we can proceed. Once the deferred objects resolve, they yield integers that we sum. So right here, we're going to say dot await all. Now we're going to change things just slightly here, and we're going to say that this is async await, and then up here we're going to do a print line async await beginning. And now instead of calling synchronous, we're going to call async await. We're going to execute the code. And we see it beginning, we see the results, we see that it took just over 1,000 milliseconds, or just over 1 second, much better than the previous 3 seconds. Being able to run our code asynchronously is incredible, but we've only scratched the surface of what coroutines can do. Increase your Kotlin skills by taking the time to study more of the capabilities of coroutines. There is a hidden danger with coroutines. What happens if a long-running task never ends? When such things happen on the main thread, the UI locking up is a clear sign that something is wrong. We have 2 ways to handle errant coroutines. Let them time out or cancel them. Let's begin with timeout. Timeouts may already be familiar to you. They are a common way to ensure that asynchronous tasks don't wait until the end of time. Kotlin makes adding a timeout trivial. Let's revisit a code snippet that makes 3 asynchronous calls to the longcalc function. Kotlin supplies the with timeout or null method. We wrap our asynchronous code with it and pass the timeout in milliseconds to it. If the code times out, we get null. Otherwise, we get the results. So right here, we're going to do a val results equals with timeout or null, and we're going to pass 600 to it, and that's going to be a long, and then we have an opening curly brace and a closing curly brace, and we're going to wrap all of our code in it. And then right here we're going to put the Elvis operator. So if it times out, we're going to get a null, and we're going to change that null into the string timed out. Then within our async block, we're going to return finished. And then just below, at the bottom of the method, we're going to do a print line results equal $ results. Now we come up here to our main method, run the function, and we get async wait beginning. We get results equal timed out, and it's just after 600 milliseconds it timed out. Now, just to be sure we didn't break anything, we're going to change this to 2,000 milliseconds because we know that this method runs in about 1 second. Rerun our code, and we get the async actually finishes. So we get 603, we get the results equals finish, and it took just a little over a second for it to run. There is a similar method named with timeout that throws an exception if the timeout is reached. If you prefer exception handling to nulls, you may want to give it a try. Canceling a coroutine, unfortunately, isn't as straightforward. Our code must actively wait for a cancellation request and exit once received. So we have a method called cancel. Cancel wraps the code in a launch block. So here's our launch block, and everything within inside of this launch block is going to run on a different thread. In the middle of this, we're going to do some work, and every 100 milliseconds or so, we're going to print out working in milliseconds. And we're going to keep running this while loop while isActive is true. To illustrate how cancellation works, let's add a couple of print lines, and we're going to add one after our while loop, And we're going to say print line canceled job. And then down here, just after we finish doing the delay, we're going to do a print line canceling job. Okay, so let's go ahead and change our main function to call cancel, run the code, and so we see that it's working. It gets the request to cancel the job, then it cancels the job, and then it ends the method. And so let's take another look at this. So this piece of code right here where we say job.cancel and join, that's sending the cancel request. Is active will turn false, and at that point it exits out of this loop. And the question might be, what is the source of is active? We're passed it via the this context of the launch block. We could write it completely out as this.isActive, but that isn't necessary. We've covered handling timeouts and cancellation of coroutines. Be sure to take a look at Kotlin's online documentation for more information. I hope you're ready for another challenge. We've seen a few examples of Kotlin's coroutines. Now, let's put them to good use. In the resources folder, there is a file, the whale.txt. Write a function to read the file asynchronously and return its text. Then, display the text to the console. Give yourself about 10 minutes to complete this challenge. Good luck. How did you do? Hopefully you came up with a solution. Keep in mind that there are many ways to solve this challenge. What is important is that your solution works, not that yours matches mine. Let's walk through my solution. So from the main function, I make a call to a function reader, which doesn't exist yet, but will shortly. From within the function reader, so I say fun reader. It doesn't take any parameters. I make this an expression block, and I say run blocking and add some curly braces. From within the curly braces, I say that val d1 equals async space open curly braces read file, and refile is another function that I'm about to write, and I pass it the underscore whale dot text. Then I do a d1 dot await, waiting for my asyncs to finish up. Then I iterate over each of the items that I've got returned, and so that's going to be a for each open and close curly braces, and then I'm going to do a print line it, and it is our default parameter. Next, we do a function read file, and this function takes in a file name, which is a string, and it returns a list of strings. And we have an opening and closing curly brace. Then we're going to say that val file equals the file object. And we know that our resources directory is at $resources/ $file name. And finally, we do a return, and that is file.read lines. And we return all of that. Then we go ahead and run our function, and we can see a whole lot of text coming from the whale. The read file function is straightforward. We read a file object using the past file name and the resources directory. We read all the lines and return them to the caller, and that's it. Async await is simple to use in Kotlin. If you'd like some extra credit, think about how to harden this code. Right now it crashes if the requested file doesn't exist. Well, we may have reached the end of this course, but this is still the beginning of your journey with Kotlin. Throughout this course, I referred to the official online documentation. It is a great resource and I highly recommend bookmarking it. In that same vein, I also recommend the Kotlin Koans. They are a series of coding challenges that you solve using Kotlin. The best approach is to use them as warm-ups before you begin your coding day. Some of them are pretty tough, so don't plan to complete them quickly. If you want to keep up with the latest Kotlin news, you may wish to check out the official blog. The Kotlin development team uses it to announce new features and future directions for the language. And finally, the best way to master any language is to use it. Kotlin is a general purpose language. Use it as much as possible every day, and soon it will become second nature to you.